Okay. Yeah. Yes, good evening to everyone. Welcome to the session. Yeah, good evening. Good evening. So, in the last class, we are completed that the we are completed the advantages of star connected armature. Okay. Yeah. And also we are completed that armature reaction, effect of armature reaction. The armature reaction is magnetization for leading power factor, demagnetization for lagging power factor. But the armature reaction is just quite opposite to the, for the case of a generator and also motor, because the current directions are quite opposite. For generator and motor, the current directions are opposite. Why? Because generator will give the current, motor will take the current. Okay, yes, for any power factor. So we have tabulated both generator and motor. So that is effect of armature reaction, right? And armature reaction can be represented with the fictitious reactants, XA. Armature reaction can be represented with XA. That is also called magnetizing reactants. And also we have seen all the various drops due to resistance, drop due to leakage reactants, and drop due to armature reaction. Then XCl plus XA, both drops are reactance drops now. So therefore XL and XA can be added. Both are in same phase. Both can be added, and that both together can be called as synchronous reactance. Synchronous reactance XS is equal to XCl plus XA. And synchronous impedance means resistance plus reactance is said to be synchronous impedance. Okay. But among them, which drop is more maximum? The drop due to armature reaction is maximum compared with all other drops. Right? Resistance can be neglected, particularly in synchronous machine. Resistance is negligibly small because armature reaction effect is more. Okay. Yeah. Based on that, we have drawn the phasor diagram of synchronous generator. Phasor diagram of synchronous generator. In generator, E leads V by delta. E leads the V by delta, because that is due to impedance drop. Fine. Yeah. Now in this class, let us start the another topic is voltage regulation. Voltage regulation of alternator. Voltage regulation of alternator. Voltage regulation. Voltage regulation of alternator. Yeah. Voltage regulation. First of all, what is the why to measure voltage regulation? Right? We are going to see what is the importance of voltage regulation. See, this is alternator. It's alternator, star connected alternator. It is supplying to a load. It is supplying to a load. It is a load. Yeah. The voltmeter reading under no load condition, the voltmeter reading V. See, this voltmeter reading is some 400 volts. Yeah. So first of all, I just wanted to define the voltage regulation. The alternator is connected. Alternator is connected with a load. Alternator is loaded. Load is adjusted to rated value, and then current is IA. IA is at rated value. Field current also at rated value. It is also rotating at synchronous speed. It is rotating at synchronous speed. A machine is operating at synchronous speed. Machine is working at synchronous speed, and it is operating at rated condition. Rated condition. Okay. Yeah. A machine supplying the rated load, armature current is rated, speed is rated, field current is also rated. Say its terminal voltage is 400 volts. 400 volts. Terminal voltage 400 volts. Full load condition. Now tell me, if I remove this load, if load is removed, then what is the ultimate reading? Tell me. Earlier, when it is connected, load is rated. Terminal voltage is 400 volts. Okay, terminal voltage is 400 volts. But when it is removed, and when load is removed, what is the terminal voltage? Terminal voltage earlier 400, now it is increases or decreases? Terminal voltage increases or decreases? Voltmeter reading increases or decreases? When load was there 400, but when load is removed, terminal voltage, the voltmeter reading increases or decreases? Tell me, increases or decreases? Any one of you respond for that? Increases, 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 decreases. It not only increases, it may be decreases also. It may be same also. When load is there, voltmeter reading 400, but when load is removed, the voltmeter reading may be increases or it may be decreases. It may be same also. Same also. Lagging power factor, if you take, for lagging power factor, definitely terminal voltage increases. For unity power factor, definitely terminal voltage increases. But leading power factor, you cannot say. Leading power factor, it may be increases, it may be decreases, it may be same also. Because voltage regulation for leading power factor, it may be positive, negative, or zero also. The no load voltage, it may be increases, decreases, or same. But how much it is changes? Definitely there is change. When load is removed, there is some change. The change is positive or negative or zero. And that how much change that can be represented with voltage regulation. Therefore, voltage regulation is nothing but it is a ratio of change in terminal voltage. Ratio of change in terminal voltage to the rated voltage when the load is removed by keeping the same excitation and same speed. So the definition of voltage regulation, it is a ratio of change in. It is the ratio of change in terminal voltage, to the rated voltage. When the load is removed, by keeping the same excitation, and same speed. By keeping the same excitation and same speed. And other things are said to be same. Therefore, voltage regulation. Regulation is equal to magnitude of E minus magnitude of V by magnitude of V. This is per unit regulation. This is said to be per unit regulation, and or magnitude of E minus magnitude of V by magnitude of V into 100. That is the percentage regulation. This is the percentage regulation. Mod E minus mod V divided by mod V. Magnitude. It is not vector difference. It is only magnitude difference. Change. What is the change? Change is nothing but no load to full load. How much change? When load is removed, that is a no load voltage. When load was there, full load voltage. So no load voltage minus full load voltage divided by full load voltage. That is the voltage regulation. Yeah. Okay. This is only just magnitude. I mean to say, see, if regulation, for example, V is equal to 400 at an angle 0 and E is equal to 450 at an angle 20 degrees, say that is delta. Then what is the regulation? Then regulation is dash. Regulation is equal to, simply you have to take 400 minus magnitude of E minus magnitude of V by magnitude of V into 100. That is nothing but simply 450 minus 400 by 400 into 100. This is equal to, you will get 12.5%. 12.5%. That will be correct. Instead of that, if you do like this, E delta minus V0 by V at an angle 0 you have taken, say, is a vector difference, no? Yes. Then it is 450 at an angle 20 degrees minus 400 at an angle 0 by 400 at an angle 0. You will get some other answer, okay, which is totally wrong. Don't do this. Don't do this one. Okay, no, this is wrong. This is wrong. Fine. Don't do like this. This is only correct. What I mean to say is magnitude. Difference is only magnitude. It's not vector difference. It's a magnitude difference. Regulation is mod E minus mod V by magnitude of V. Okay. Yeah. And he has given once in an examination. But there are also different type of voltage regulations are there, na? E minus V by V or V minus E by E. The alternator voltage regulation is mod V minus mod V by mod V. The voltage regulations, there are two types, no? Regulation E minus V by V into 100. This is what? Regulation up. We will say regulation up. And that is also equal to E minus V by E into 100. That is regulation down. Regulation down. But for alternator, this is only for alternator regulation up only we will take. If you take transformer, we will take it as a regulation down. Regulation down. Correct? E minus V by V. So this is alternator, but this is for transformer. So alternator, you need to take only E minus V by V divided by V. So in one particular examination, question is given like that. The question is voltage regulation of alternator. Voltage regulation of alternator. Alternator is a bit E delta minus V0 by V0, okay, into 100% or simply. Okay. Next, B bit E delta minus V0 divided by V, that is a V0, and C bit magnitude of E minus magnitude of V divided by magnitude of V and D bit mod E minus mod V by mod E. Okay. So what is the answer? That answer will be, this is only correct. Right? Is only correct. This is E at an angle delta. At an angle delta. Okay? Yes. So it is only magnitude of V. In an alternator, why V to be taken? Here the point is, in alternator we are taking V. Transformer you will take E. Okay. In alternator In alternator, regulation down, regulation up to be taken, In transformer, regulation down to be taken. Okay. Why to take regulation up in alternator, transformer regulation down? Right? Because reason is, in alternator, in transformer, and the nameplate details given, they are the no load voltages, no load EMF. Because full load voltage cannot be given in transformer. In transformer, can you give the full load terminal voltage? No. The nameplate details, they are given only no load EMF, E1 by E2, V1 cannot be given. Why? Because load voltage changes. For example, you are writing on the nameplate details that voltage can be maintained. For example, V is given, say, for example, V is some 230 volts. No load also you can maintain 230, full load also you can maintain 230, off load also you need to maintain 230. In other words, transformer, you cannot control the voltage, you cannot maintain the voltage. If you take alternator on the nameplate details given, there will be only, right, V will be given. For example, I want for my alternator, it is 400 volts. Off load also I can maintain 400, full load also I can maintain 400, right? And one and a half load also I can maintain 400. How you can maintain the terminal voltage? Even the load changes, right? The terminal voltage can be maintained by changing the field excitation. By increasing or decreasing field excitation, I can maintain the terminal voltage. That's the reason I can give the V. V can be mentioned on the nameplate details because V can be maintained constant. But in transformer, can you maintain the V constant? No. As load changes, terminal voltage changes, V changes. Can you control that V? You cannot control. We cannot control. Right? Yes. You cannot control. That's the reason V cannot be given. E can be given. E, no load voltages are always same. No load voltages are same. Okay? Yeah. On the nameplate given, it will be always terminal voltage. Okay. Now, first of all, why to measure the voltage regulation? What is the necessity to measure the voltage regulation? Let us see. Necessity to measure the voltage regulation. Necessity to measure the voltage regulation. What is necessity to measure the voltage regulation? The necessity is, so for example, alternator is there. This alternator. Okay. When full load condition, for example, alternator is operating at full load condition. When load is connected, okay, its terminal voltage is some 400 volts, say 400 volts is the load, 400 volts, full load condition 400 volts. Fine. But when the load is removed, it is full 400 volts. But when load is removed, say, how much rise in voltage? How much rise in its terminal voltage? When load is removed, say, the voltage may be increases, voltage may be increases to some 600 volts, or it may be increases to 700 volts, like that. But when, how much change is there, that you should know. It gives the information for the selection of the voltage rating. So how much voltage you can take? Can you take for the voltage insulation rating? Insulation rating can be taken for no load or full load voltage. No load voltage. So full load 400 volts. When load is removed, it is 400, 600, 700, 800. That you should know, because based on that 800 volts only, rating of the insulation will be selected. So first one is the regulation gives. First one, number one, the regulation, voltage regulation gives information. Voltage regulation gives the information for the selection of rating of insulation. For the selection of rating of insulation. How much change it is coming? That rating of selection of insulation, number one. And the second one is it gives the information for the selection and design the AVR, automatic voltage regulator. It gives the information. It gives the information or data. It gives the information to design and select the AVR. What is that AVR? That is said to be automatic voltage regulator. Automatic voltage regulator. That is nothing but field regulator. Automatic voltage regulator means this field current can be controlled. Actually, in practical cases, in generating stations, say there is automatic voltage regulation, AVR. AVR, what it will see? It will see the always output voltage. Closed loop system, output voltage, and it take the feedback signal. Always it identify the terminal voltage. For example, you are setting it is 400 volts. Okay. When load is reduced, say, when load is half load, voltage is increased. How much increasing? It will take the information. Based on that, it will increase the field current or decrease the field current. And when load is increased, 1.5 load, say, voltage drop. How much voltage drop? That you should know. Based on that only, the field regulator will increase the current. So while you are designing the field regulator, you should know half load, what is the drop? Full load, what is the drop? 100 load, what is the drop? 25% of the load, what is the drop? If you can calculate all the voltage regulation for various loads, and that data will be used to design, right? To design the AVR, automatic voltage controller, automatic voltage regulator we can design. For that, data must be known. Based on that data only, you can program it. For example, load is decreased to half load, increase the field current this much. When load is increased to 2/3 of the load, what to do? Information. The voltage regulation is now you can feed the data for AVR. And third one is it affects the voltage regulation, affect the parallel operation of alternator also. Parallel operation of alternators. And during parallel operation, synchronous reactance is there, XCS. XS is the main component for stable parallel operation. When XS is more, say regulation is more. Regulation is depends upon what? Impedance, reactance. Voltage regulation affect the parallel operation. And fourth one, voltage regulation also affect the stability. All these are the things. But last 3 and 4 we are going to see at the time of parallel operation, how regulation, the stability also depends on the regulation, and parallel operation also depends on the regulation. Okay, and that depends on the XCS. Fine. So this is the question. Last 3 years back, you can find a question on this. Which of the following statements are correct regarding the voltage regulation? As given, Necessity of voltage regulation. Statement is also necessity of voltage regulation. Statements are given directly. Statement 1, 2, 3, 4. These 4 statements will be directly given. Right? And among that, A bit 1, 2 correct, 1, 2 or 2, 3. Okay, what is the necessity for all these things? All the above. All these 4 statements. Okay, 4 statements is given. You can see it's direct statements. The direct statements means I have taken from these statements from P.S. Bimra. P.S. Bimra textbook, it is there. You please see that. Okay, not necessary. It has given already. Sorry, 1 minute. Okay, fine. Now, then voltage regulation, range of voltage regulation. Range of voltage regulation. In alternator, range of voltage regulation, it is 30 to 40%. 30 to 40% or even more. Even more. In some cases, and generally it is 30 to 40%, but in some cases, in some alternators are designed. Some alternators are designed. Some alternators are designed with voltage regulation. With voltage regulation 60 to 70%. With voltage regulation 60 to 70% or even more. Or even more. To limit the short circuit current. To limit the short circuit current. To limit the short circuit current. Short circuit current. That is for self-protection. For self-protection. They are designed with more voltage regulation. More voltage regulation means large ZS. They are designed with more voltage, 60 to 70% or even 80% like that. See how it is that we know regulation is equal to E minus V by V into 100. Okay, that is equal to what? IA into ZS. Say roughly. Of course, it's the phasor difference. IA ZS divided by V into 100. Say approximately. IA ZS divided by V. The regulation is proportional to ZS, na? Yes, regulation is proportional to synchronous impedance. When regulation is more, drop is up. ZS is more, drop is more. When ZS is more, drop is more. Therefore, regulation is depends on the impedance ZS. Okay? Yes. Similarly, if alternator, it is short circuited, say. Is alternator, it is short circuited, right? All terminals are shorted. Then the generated EMF E, what it will do? It will drive the short circuit current ISC. It drives the short circuit current ISC. Then actual equation E is equal to V plus IA ZS. But under short circuit condition, V is equal to 0 and IA is equal to ISC. Okay, when terminals are shorted, all 3 terminals are shorted, then short circuited, that V will be 0. Terminals are shorted, na? Yes. This is V0 here. Here V0, na? Yes. Terminals are shorted, V0. Current is equal to IA is equal to ISC. So therefore, what is this? E is equal to, simply it is ISC into ZS. Now what is ISC? IS is equal to E by ZS. This is a short circuit current. Short circuit current is equal to voltage divided by impedance. Why? Because V0. V0 means actually current is E minus V by ZS. Current is equal to E minus V by ZS. But V0, E by ZS. So what we are doing is, what we are doing, when short circuited also, it has to be limit the current. Even short circuit also limit the current means we will design with large value of ZS. When ZS is large means IS is less. It limits the short circuit current and self-protection. Even alternator short circuit also self-protection. So they will design with large value of ZS to limit the short circuit current. But when ZS is more, regulation is more. When ZS is more, regulation is large. But I will ask one point for you. When ZS is more, is there any effect on the efficiency? Efficiency, is there any problem with efficiency? No. There is no problem of efficiency. Because impedance, what is there? Mainly reactance. Resistance can be neglected. In our synchronous machine, resistance can be neglected. Reactance. But where reactance is there, there is no power loss. There is no power loss. When regulation is more means poor regulation, fine, accepted. But no effect on the efficiency. Efficiency is not affected. Okay. Yeah. Large value of reactance. See, the large value of reactance. The machines are designed. The machine is designed with. The machine is designed with large value of ZS to limit the short circuit current. To limit the short circuit current. Short circuit current. Yeah, short circuit current. But regulation is proportional to ZS. Therefore, regulation is more. Regulation is more. Regulation is more. Okay, regulation is more. But self-protection for the machine. But self-protection towards the. But self-protection. Self-protection against the short circuit. Against the short circuit. Even short circuit occurs also, nothing will happen. That is the thing. But only if you want 400 volts means more generated voltage, you need to generate more voltage. You need to generate more voltage. So for example, you want 400 volts means your generated voltage must be large. For that, what will it require? More number of turns is required. More cost of the insulation. Size of the machine is more. Size of the machine is more. Cost increases. But self-protection only. Self-protection. Cost, size, insulation. You want 400 means more drop means more EMF you need to generate. Correct? Yes. But some alternators for self-protection, cost, all these things does not matter. Main thing is self-protection, they will design. Okay. But no effect on the efficiency. Though no effect on the efficiency. No effect on the efficiency. No effect on the efficiency. Because no power loss. No power loss in synchronous reactance. No power loss in synchronous reactance. Only voltage drop. Only voltage drop. Okay. Voltage drop takes place, but no power loss in that. Efficiency reduced means nobody will accept. Regulation, I do not bother. You want 400 volts means I will supply for you. For that, I need to generate more voltage. I want more number of turns, more insulation, more size of the machine. Okay, my machine definitely poor regulation, size cost more. But you want 400, I can give. For that, I need to generate the 800 volts. Does not matter. Okay. Self-protection. And one examination, the question is like this. Question is, The voltage regulation of an alternator. The voltage regulation of an alternator. Voltage regulation alternator compared with equivalent rating of transformer. Compared with equivalent rating of transformer. Equivalent rating of transformer is A bit much more, B bit much less, C bit equal E bit. Data insufficient. Data insufficient. Yeah, what is the answer? The voltage regulation of an alternator compared with voltage regulation of voltage regulation of an equivalent rating of transformer. Compared with voltage regulation of equivalent rating of transformer is. So voltage regulation of alternator is much more compared with the transformer. Okay. In transformer, regulation is 5%, 6%. Okay. Transformer regulation 5%, 6%, hardly 10%. But alternator regulation is 30%, 40%, or even more, 60%, 70% also. Much more. Regulation of alternator is much more. Why reason? Why alternator will have more regulation? Because drop due to armature reaction is extra in alternator. That is much more. Transformer, there is no armature reaction. Yes, there is no armature reaction. So the thing is here, drop due to armature reaction. Drop due to armature reaction. Drop due to armature reaction is much more. Drop due to armature reaction is much more. That is extra. First of all, drop due to armature reaction is extra. It is not there in the transformer. Extra. Drop due to armature reaction is extra in alternator. In alternator, which is much more. Which is much more. Okay. Fine. Now, just a minute. Oh. Because in transformer there is no armature, no? Only resistance drop, leakage reactance drop. But whereas here, resistance, leakage reactance drop is very less. Armature reaction is maximum. Okay. Next, so the problems on the voltage regulation is quite common, and objective questions also quite common. Some objective questions will be conditionally based objective question, conditionally based. Common sense type of questions. Common sense. He will give some data, 4 options. Among 4 options, you need to select any one option. No data, nothing will be given. Some question, only 4 options, you have to select one appropriate answer. How you can select? Having idea about the machine, having the prior knowledge. Having prior knowledge, you can choose one option. Okay. So for that, it is required knowledge of condition for zero regulation, conditionally based problems also. Condition for zero regulation, condition for maximum regulation. Based on that, I am going to draw the regulation curve. Regulation curve, and after that, we are going to see the objective questions. Okay. A very important discussion we are going to start now. Condition for voltage regulation curve. All theoretical questions, common sense type of questions can be answered by drawing the voltage regulation curve. So that we are going to draw by taking the conditions. Minimum voltage regulation, maximum voltage regulation. See, condition for minimum regulation. Condition for zero regulation. Zero regulation. That is minimum regulation. Condition for minimum regulation. Zero regulation. Voltage regulation will be zero, positive and negative also. Zero regulation. First of all, zero regulation can be obtained only for leading power factor. Zero regulation can be obtained. Zero regulation can be obtained for leading power factor. Leading power factors. Zero regulation only for leading power factors. Lagging power factor always regulation is positive. UPF also positive. But leading power factor it may be positive, negative, zero. So zero regulation can be obtained. Zero regulation can be obtained only for leading power factor. Can be obtained only for leading power factor. Power factor. Why? Reason. Reason. Why reason? Reason. Let me compare with lagging. Why not lagging? See, E is equal to square root of V cos phi plus IARA whole square plus V sin phi. This we have got expression last class, na? Yes. Plus or minus IA into XS whole square. V cos phi plus IARA whole square. V sin phi plus or minus IA XS whole square. Plus for lagging power factor, minus for leading power factor. Plus lagging, minus leading. First let us see with the lagging power factor. If it is lagging power factor means, for lagging power factor, both resistance causes drop of voltage. Reactance also causes drop of voltage. Both causes drop only. Resistance causes drop. Reactance means demagnetization. It is also causes drop of voltage. When drop means drop of voltage, so both drop means definitely V will be less than E. No load voltage 450 volts say. When load connected, drop only and the voltage will be less than 450. When load connected, V always less than E. Therefore, regulation is always positive for lagging power factor. When load connected, voltage is only drop, reduces. So full load voltage always less than the no load voltage. So that's the reason V always less than E. Regulation is always positive for lagging power factor. See, for lagging power factors, IARA causes drop of voltage. IARA causes drop of voltage. Or resistance, say, instead of IARA, resistance, RA causes drop of voltage. Causes drop of voltage. And reactance also causes drop of voltage due to demagnetizing effect of armature reaction. Excess causes drop of voltage. Due to demagnetizing effect of armature reaction. Demagnetizing effect of armature reaction. Armature reaction. Excess is mainly armature reaction. Yes. Due to demagnetizing effect of armature reaction. Since both are the drops. Therefore, V always less than E. As load increases, voltage decreases only. As load increases, V decreases only. So therefore, V always less than E. When V always less than E, then what is the regulation? Therefore, regulation is equal to E minus V by V into 100 is always positive. Is always positive for lagging power factor. Is always positive for lagging power factor. So lagging power factor always regulation is positive only. Always positive for lagging power factor. Whereas for leading power factor, if you take leading power factor, see, this is taken now. Yeah. For leading power factor, see for leading power factors. For leading power factor, E is equal to, what is the equation? E is equal to square root of V cos phi plus IARA whole square. V cos phi plus IARA whole square plus V sin phi minus IAXS whole square, correct? Minus IAXS whole square. Due to that, resistance causes drop only, resistance causes drop. But reactance causes rise of voltage. This is causes rise. Rise. Why? Due to magnetization. Magnetization effect of armature reaction. Due to magnetization of armature reaction, voltage increases. Earlier, demagnetization means voltage reduces. Resistance causes drop, but reactance causes rise of voltage. Rise of voltage. For example, can you tell me, drop is 20 volts, rise is also 20 volts, rise also 20 volts. What is the net drop? Tell me. Net drop is 0. Net drop 0. Due to resistance 20 decreases, due to reactance, armature reaction 20 increases. 20 drop, 20 rise. Net drop is 0, then voltage regulation is 0. But earlier both are drop only. Both are drop ante, both the drop of the voltage is sum of the drop. But here it is difference of the drops. Difference may be 0. Sum never be 0, na? Yes. So if drop due to, if rise of voltage due to reactance is equal to, rise of voltage due to reactance is equal to drop due to resistance. Net drop is 0. Regulation will be 0. In other words, for leading power factor, resistance causes, RA causes drop of voltage only. Causes drop of voltage. XS causes rise of voltage. Causes rise of voltage. Causes rise of voltage. Because due to magnetizing effect, due to magnetizing effect of armature reaction. Magnetizing effect of armature reaction. Now, if drop due to, if rise of voltage due to, drop rise both are equal. If rise of voltage due to XS, rise of voltage due to XS is equal to drop due to resistance, drop due to RA, then the net drop will be 0. Then the net drop will be 0. Net drop will be 0. Then the regulation will be 0. Drop rise both are equal. 20 decreases, 20 increases volts. Net is 0. Then the net drop will be 0. Net drop will be 0. Net drop will be 0. Okay. Then regulation is 0. Then regulation will be 0. Regulation is equal to 0. In other words, it is like this. If rise of voltage rise of voltage due to IAXES is equal to drop due to IARA. Drop due to IARA. Then regulation will be 0. Regulation is 0. Rise of voltage is equal to drop due to resistance. Regulation is 0. Then regulation will be 0. If rise of voltage is greater than the drop due to IARA, then the regulation will be negative. The rise is more. As load increases, voltage increases, rise is more. The V increases, regulation will be negative. If rise of voltage is less than the drop due to IARA, then regulation will be positive. Positive. So 3 cases arises. How much rise? It is depends on the power factor of the load. The pure capacity load you take, regulation is positive. More rise, more rise. So for leading power factor, regulation may be positive, negative, 0. 3 cases occurs. How much rise is a matter. Fine. Now let me take the condition. Have taken? Okay. So now let us simplify it. Let us get the condition. Condition. So we are going for condition. See. E is equal to, what is that? E is equal to square root of V cos phi plus IARA whole square plus V sin phi minus IAXS whole square. Now squaring on both sides, square. E square is equal to V cos phi plus IARA whole square plus V sin phi minus IAXS whole square. Simplify. Expanding the first term, V cos phi plus IARA whole square by expanding V square cos square phi plus IA square RA square plus 2V IARA cos phi. 2V IARA cos phi plus V square sin square phi, extending second term, plus IA square XS square minus 2V IA XES sin phi. IA XS sin phi. Okay, this E square expanding. Now add these things, add both. So therefore, by adding both, first one, these two, V square cos square phi plus V square sin square phi is equal to how much? V square, simply V square. So this is V square plus, what about these things? IA square RA square plus IA square XS square is equal to how much? IA square ZS square. That is IA square ZS square. ZS square plus 2V IA common in these terms, 2V IA common, 2V IA into RA cos phi minus XES sin phi. RA cos phi, XES sin phi. So that is equal to V square plus, again further simplification, V square plus IA square ZS square plus 2V IA RA, let us write ZS cos theta. Do you remember in the last class? RA, this is RA, na? This is RA, this is XES, this is ZS. What is this? This is theta. So therefore, RA is equal to ZS cos theta. XS is equal to ZS sin theta. So based on that, I am writing. This already we have seen, no? Yes. So therefore, RA, in the place of RA, I am writing Z as cos theta, cos phi. E square plus IA square, IA Z square, 2V IA Z as cos theta cos phi, XS is equal to Z as sin theta and sin phi. Sin phi. And further simplification, V square plus IA square Z square plus 2V IA. Z is also common, na? Z is also common. And cos theta cos phi minus sin theta sin phi is equal to cos of theta plus phi. Theta plus phi. Theta plus phi. And there is also equal to V square plus IA Z is also common. IA Z is also common. That is IA into ZS plus 2V cos of theta plus phi. Theta plus phi. E square. So E square minus V square. I am bringing V square this side. That is equal to what? IA into ZS into IA into ZS plus 2V cos of theta plus phi. So let me take this equation. I want this equation. Finally, we have got this. E square minus V square is equal to IA into ZS. IA into ZS plus 2V. Okay. Now, for zero regulation, what it is required? For example, I want regulation to be 0. So for zero regulation, E square minus V square is equal to 0. 0. Because E is equal to V. E is equal to V. Therefore, equate this E square minus V square is equal to 0. E square minus V square is equal to 0 for zero regulation. In the next page, that is what I am going to do. Fine. Yes. E square minus V square is equal to what we are having? IA into ZS and IA into ZS plus 2V cos of theta plus phi. That is equated to 0 for zero regulation. 0. But in that, the first term is not 0. Only inside of the bracket we can equate to 0. This will become 0. Okay. Therefore, IA ZS plus 2V cos of theta plus phi is equated to 0. Okay. Yes. When that is 0 means, what is the condition? Cos of theta plus phi is equal to minus IA ZS divided by 2V. So this is the condition. Condition for zero regulation. Condition for zero regulation. Cos theta plus phi is equal to minus IA ZS divided by 2V. Fine. Now, then similarly, get the expression for condition for maximum regulation. Maximum regulation. Condition for maximum regulation. This is 0, na? Yes. Next. Let us see condition for maximum regulation. Over. Now, condition for maximum regulation. Condition for maximum regulation. Maximum regulation can be obtained for lagging power factor. Maximum regulation can be obtained maximum regulation can be obtained for lagging power factor. For lagging power factor. Why reason? Reason. What is the reason? Why it is for lagging power factor? Maximum regulation. Why not leading power factor? Though it may be negative, but maximum regulation is only for lagging power factor. Reason is, for leading power factor both drop and rise, whereas for lagging power factor both are drop. Okay? Listen to me. For let me compare leading power factor, lagging power factor. For leading power factor, resistance causes drop, reactance causes rise. So what is the net drop? Net drop is difference of both. Net drop is difference of both. But whereas for lagging power factor, both resistance causes drop, reactance also causes drop. So when both are the drop means net drop is sum of both. Net drop is sum of both for lagging power factor. So sum is always more than the difference. Na? For leading power factor, difference. Lagging power factor, sum of drops. So sum of drop is always more than the difference of both. Therefore, regulation is more for lagging power factor. To take any same power factor, any load condition, regulation for lagging power factor will be more. So the meaning is, for leading power factor, resistance causes drop, RA causes drop, and excess causes rise. Excess causes rise of voltage. The net drop is difference of both. The net drop is difference of both. Right? But for leading power factor, this is for lagging. For lagging power factor, RA causes drop. Excess also causes drop. Drop of voltage. Excess also causes drop of voltage. Therefore, the net drop is difference of both. Net drop is sum of both. Okay, net drop is sum of both. But sum of drop is sum of both, which is always more than the difference of both. For leading power factor. Difference of both for leading power factor. Therefore, voltage regulation is always more. Voltage regulation is always more for lagging power factor. Compared with leading power factor. Okay? Yes. So, regulation is more for any power factor. Regulation is more for lagging power factor. Therefore, maximum regulation also will be for lagging power factor. Maximum regulation will be for lagging power factor. Maximum regulation is for lagging power factor. Now with the same thing, do the same analysis. See, this is very clear now. Yes, both are the drops. Both are the drop means net drop is more. Leading power factor difference always less. Sum is always more. And for this, E is equal to E is equal to what? Lagging power factor. So for lagging power factor, E is equal to V cos phi plus IA RA whole square plus V sin phi plus IA XS whole square. Lagging power factor plus IA XS whole square. That is equal to, now squaring on both sides, E square. E square is equal to V square cos square phi plus IA square RA square plus 2V IARA cos phi, IARA cos phi plus expanding second term V square sin square phi plus IA square XS square plus 2V IA XS sin phi. Sin phi. Now add these both. By adding these two, V square is equal to, this is V square. Cos square phi plus sin square phi is equal to 1 na? Yes. V square plus the second term is IA square ZS square. RA square plus XS square is equal to ZS square plus 2V IA common. 2V IA common. Again RA cos phi plus XS sin phi. XS sin phi. We are doing same analysis, only instead of plus it becomes a minus, it becomes plus for lagging power factor. Together V square plus IA square ZS square plus 2V IA. Instead of RA, we are writing ZS cos theta. This is cos phi plus ZS sin theta, sin phi is equal to V square plus IA square ZS square plus 2V IA into ZS common cos of theta minus phi. Okay. Are you getting difference between theta and phi? Theta is impedance angle, phi is load power factor angle. Theta minus phi. So that is equal to V square plus IA into ZS common, that is IA into ZS plus 2V cos of theta minus phi. Okay. So finally, E square minus V square is equal to what? E square minus V square is equal to IA into ZS, IA ZS plus 2V cos of theta minus phi. Now I need this relation. Same explanation. But earlier what you have got? Same equation only. Whereas cos theta plus phi we have got. Now it is cos theta minus phi. Cos theta plus phi. Now it is cos theta minus phi. Cos theta minus phi. Okay. And if you want for maximum regulation, what to do? D E square minus V square by D phi. That will be equated to 0 with respect to power factor. We are going to differentiate with respect to power factor because regulation is depends on the power factor. Of course, regulation also depends on the load current also, but current we are taking same. IA to be taken rated value based on the power factor. Power factor load may be 0.6 lagging, 0.8 lagging. Okay. 0.8 lagging also we can have 20 amperes. 0.6 lagging also you can have 20 amperes. Mainly we are considering with respect to phi. Differentiate with respect to phi. D square E phi by DE square. Now I am equating. So what we have got? E square minus V square is equal to IA into ZS, IA into ZS plus 2V cos of theta minus phi. This we have got. Now for maximum regulation, d square differentiation. Differentiate this and equal to 0. d phi is equal to, this is IA into ZS, this term 0. I am taking IA as a constant. IA constant 0 plus 2V sine of theta minus phi that is equated to 0. Okay. 2V. This is cos. Differentiation of cos is minus phi, minus, but phi also minus is there. That's the reason it is minus into minus plus. Some student may be getting a doubt. Sir, cos value differentiation is minus psi. Okay, correct, minus. But phi also minus is there, na? Minus 1. Both becomes plus. But this is not equal to 0. Only inside of the bracket will be 0. So from this, what we can say, 2V sine of theta minus phi is equal to 0. 2V sine of theta minus phi is equal to 0. But 2V never be 0, na? 2V never be 0. Sine theta minus phi is equal to 0. Sine theta minus phi is equal to 0. That should be equal to sine 0 degrees. Sine value, sine 0 is equal to 0. Of course, sine 180 also equal to 0. But it will be always equated to 0. Can you tell me why it is not sine 180 0? Bro, can I equate this is equal to sine 180? Is it correct or wrong? Wrong, no. This will be wrong. Why? Tell me. Why? Tell me. Why it is? Why it is? Is it correct? Reason is theta maximum how much? Theta maximum value is 90. Theta maximum is 90 degrees. It is less than or equal to 90. Theta will be less than or equal to 90. What is the phi value? Less than or equal to 90. The power factor angle is not more than 90. So therefore, what will happen? Theta minus phi will be always less than or equal to 90 only. 90 only. Okay. Theta plus phi will be less than or equal to 180. This is only possibilities. These are only possibilities. Correct? Yes. Theta less than 90. That's the reason it is theta minus phi. I am taking theta minus phi. When minus phi means theta minus phi will be always less than 90 only. Theta ne maximum 90. Are you getting? Theta itself maximum 90. 90 minus something is less than 90. Na? Therefore, how it becomes 180? No. It is sine 0. Sine 0 only correct. Yeah. From this, theta minus phi is equal to 0. Theta minus phi 0. Therefore, phi is equal to theta. This is the condition. This is the condition for maximum voltage regulation. Maximum voltage regulation. Condition for maximum voltage regulation. Okay, phi is equal to theta. Phi is equal to theta. Then what is that? Impedance angle is equal to load power factor angle is equal to impedance angle. Load power factor angle is equal to impedance angle. Right? Load power factor angle is equal to impedance angle. Fine. Now, so based on these conclusions, we are going to draw the regulation curve. Let us see what are the possibilities. For which range of power factor you can get the zero regulation, and which range of power factor you will get voltage regulation in maximum. Common sense I told na. And you can expect answer by knowing the conclusions. Let us see that. So, yeah, I want to do small analysis. Based on that, we will give the conclusions. See, maximum regulation, condition for zero regulation. Condition for zero regulation is cos of theta plus phi. Condition for zero regulation. Condition for zero regulation is cos of theta plus phi is equal to minus Ia Zs divided by 2v. Condition for zero regulation, cos theta plus phi is equal to minus Ia Zs divided by 2v. This we know condition. Okay. From this, what we want to do is Ia Zs is very, very smaller compared with 2 times of rated voltage. See, in the denominator it is 2 times of rated voltage, but in the numerator it is Ia Zs. Therefore, Ia Zs drop is less compared with 2 times of rated voltage. Therefore, cos of theta plus phi, I will take cos of theta plus phi is nearly equal to 0. Is nearly equal to 0. Fine. Yes. Nearly equal to 0 means, yeah, this is denominator Ia Zs divided by 2v is nearly 0. That is cos theta plus phi is nearly 0 means that is equal to how much? Cos 180. Not cos 180, cos 90. Correct? Cos 90. Cos 90 0, cos next, cos 270 0. But theta plus phi never be 270. Correct? Cos theta plus phi 0 means cos 90 0, cos 270 also 0. But 270 is not correct. Cos 90 only correct. Okay. So therefore, theta plus phi is nearly equal to 90 degrees. Then what is phi? Phi is equal to 90 minus theta. 90 minus theta means 90 minus theta how much? Some 80 degrees say. Yesterday I have given theta. What is the value of theta? 80 to 85 degrees. You remember? Theta 80 to 85 degrees. So 90 minus 10. How much it is? Nearly 10 degrees say. 10 degrees. Then what is the power factor? Power factor is equal to cos phi. Cos phi means it is cos 10. Cos 10 is equal to how much? Nearly it is 0.98 leading. 0.98 leading. Which is very closer to, this is almost closer to UPF. Closer to UPF. This is closer to UPF. Closer to UPF. Almost 1. 0.98 lagging means how much? Leading means how much? Nearly 1. So, the conclusion from this is, don't say it is, I am not I am not saying that always zero regulation is for 0.98 leading. No. Roughly I am saying it's closer to 1. Leading power factor closer to 1. So the conclusion is like this. The zero voltage regulation can be obtained for the leading power factors which are closer to 1. But not equal to 1, but not UPF. Closer to UPF, but not UPF. UPF always regulation positive. Okay, closer to UPF. They are said to be lightly capacitive loads. Light capacitive loads. So pure capacitive load means it is ZPF leading. Pure capacitive load means it is zero side. Nearer to 0, pure capacitive, but it is nearer to 1. Nearer to 1 means light capacitive loads. Light capacitive. Zero regulation, 0.95 leading, 0.96 leading, nearer to 1. Okay, let me write the statement. The zero voltage regulation can be obtained. So the zero voltage regulation. Zero voltage regulation can be obtained. The zero voltage regulation. Regulation can be obtained. Can be obtained for leading power factors. For leading power factors which are closer to UPF. Closer to UPF. For example, 0.95 leading or 0.96 leading, etc. 0.98 leading, etc. 0.96 leading, etc. 0.95, 0.96 leading, etc. etc. Okay. They are said to be lightly capacitive loads. They are said to be lightly capacitive loads. Light capacitive loads. Okay. Light capacitive loads. Similarly, condition for maximum regulation, if you see. Condition for maximum regulation. So this is closer to UPF, nearer to 1. So clear? The 0.95, it is almost nearer to 1. Generally, capacitor load regulation negative only. We can use 0.98 leading type of load, where you can use. Instead of that, better use UPF. What is 0.98 leading means almost 1. Practically, they are not used. Practically, regulation for leading power factors negative only generally. But if it is very closer leading power light capacitor loads, there is a choice of regulation. Zero regulation. Okay. Similarly, and we have got condition for maximum regulation. Condition for maximum regulation, phi is equal to theta. Phi is equal to theta. Load power factor angle is equal to impedance angle. But how much it will be? Some 80 to 85 degrees. Say roughly, I am taking just for understanding purpose, numerical values. Nearly 80 say. Therefore, what is the power factor? Power factor is equal to cos phi. Cos phi means it is cos 80. Cos theta is equal to cos 80 say. How much it is? 0.17 lagging. 0.17 lagging. This is closer to ZPF lagging. Closer to ZPF lagging. Closer to ZPF lagging. But earlier one closer to UPF. Zero regulation is closer to UPF. But this is closer to ZPF lagging. 0.1 lagging, 0.2 lagging. Okay. Closer to ZPF lagging. These are said to be pure inductive load. Almost inductive load. 0.1, 0.2 lagging. Almost ZPF lagging. Highly inductive load. Can I say this type of loads? Pure inductive loads. Pure inductive loads means highly inductive loads. Highly inductive loads. Therefore, the conclusion is zero maximum regulation. Maximum regulation can be obtained for the leading power factors. Sorry, for the lagging power factor closer to ZPF lagging. Lagging power factor closer to ZPF lagging, like 0.1 lagging, 0.2 lagging, etc. They are said to be highly inductive loads. Highly inductive loads. Pure inductive loads. Maximum regulation for pure inductive loads you will get. So the statement is the maximum voltage regulation can be obtained. The maximum voltage regulation can be obtained for the lagging power factor loads. For the lagging power factor loads which are closer to ZPF lagging, For example, 0.1 lagging, 0.2 lagging, etc. Okay, they are said to be highly inductive loads. They are highly inductive loads. Pure inductive loads. Right? Pure inductive loads. If RA neglected, what will happen? Tell me. If RA neglected theta 90, then cos 90 is zero lagging. If RA neglected, maximum regulation is for ZPF lagging itself. ZPF lagging only. See, make a note. If RA is equal to 0, say RA 0, then what is theta? Theta is equal to 90 degrees. Theta is equal to tan inverse of XS by kada. Theta is equal to tan inverse of XS by RA. We remember? Yes. But if RA is equal to 0, theta 90. Then what is the regulation? Then regulation is equal to, then power factor is equal to, what is the power factor? Then power factor is equal to cos phi. That is cos theta. That is how much? Cos 90. Cos 90 means this is itself ZPF lagging. Therefore, if resistance is neglected, if RA neglected, the maximum regulation will be for ZPF lagging itself. For ZPF lagging only, you will get maximum regulation. If resistance is neglected, resistance 0, it will be for maximum regulation. Will be for ZPF lagging only. Okay. Based on these conclusions, let us draw the regulation curve. Okay. Regulation curve. Important thing here is maximum regulation is for closer to ZPF lagging. Zero regulation closer to UPF. So with these statements, let us draw the regulation curve, voltage regulation curve. Okay. Voltage regulation curve. Voltage regulation curve. Voltage regulation curve. Voltage regulation curve means regulation versus power factor, because we are doing analysis based on the power factor. See, this is positive regulation. This is negative regulation. And this is lagging power factor. This is leading power factor. This is one UPF, unity power factor. unity power factor. This is UPF, say this is 0.8 lagging, this is 0.6 lagging, 0.4 lagging, 0.2 lagging, this is 0 lagging, ZPF lagging. Similarly, 0.8 leading, 0.6 leading, 0.4 leading, 0.2 leading, this is 0 leading, 0 leading. 0 leading. Now on this, locate our conclusions. We have drawn that conclusions earlier. Substitute those conclusions in this. Substitute the conclusions here. Okay, y-axis regulation, x-axis power factor. Right side lagging power factor, left side leading power factor. Important thing is, you have taken this now? Yes. Listen. Important thing is, these two are important. What we have observed, see, 0 regulation can be obtained for the leading power factor which are closer to UPF, 0 regulation closer to UPF. And almost 0.98 leading like that, 0.8 leading, 0 regulation. But maximum regulation can be closer to ZPF lagging, A 0 regulation closer to 1, maximum regulation closer to ZPF lagging. So let us put these 2 points in our diagram. See, so 0 regulation will be this side, yes, 0 regulation on leading side, leading power factor, but it is closer to 1. Leading side, but closer to 1. So this is 0 regulation 0, say. But when regulation is 0, it will be point on the x-axis, because y-axis regulation, y component 0, regulation 0. So it will be point on the x-axis, but closer to 1. Plus 0 regulation. This is the first point, 0 regulation for leading side, but closer to 1. Whereas for lagging power factor, maximum regulation is for lagging power factors. For this, say, 0.1 lagging, for example. So for that, is regulation will be maximum. Regulation is maximum, say. For this power factor, regulation maximum. Now join these two. Extend this here. This is the regulation curve. Okay. Regulation curve. I think you will be familiar with this. You might have done similar analysis in transformers. Okay, transmission line. Here also it is similar. But here synchronous impedance is there, na? Transformer, no synchronous impedance, nothing. The regulation curve. Regulation is maximum closer to ZPF lagging, 0 for this leading side. Leading side for closer to UPF. Now, and observation, see, from this curve, for unity power factor regulation always positive, for UPF regulation always positive, but leading power factor maybe regulation maybe here it is positive also, regulation positive, regulation 0 and regulation negative also. For leading power factor, regulation positive, negative, 0. 3 cases that is happening. But UPF always positive, lagging also always positive. So from the graph, the voltage regulation is always positive. The voltage regulation is always positive for UPF and lagging power factor. Lagging power factor. But the voltage regulation may be either positive, maybe either positive, negative, or zero for leading perfectors. For leading perfectors, it's all possible. For leading perfectors, correct? Yes. For leading perfector, regulation may be positive, negative, or zero. Lagging perfector is positive. Fine? Okay. Yeah. Now let us see the questions on this. As I told, common sense type of questions without any data, you can answer for this type of questions. Let us see. The questions are, I would like to give for each model one question. And whatever I am going to give, they are one of the examination questions only. One of the examinations. It's not gate. Some questions are gate, some is IAS, some is some. All varieties of questions, each one. But after having idea about this curve, those questions are quite simple. Let us see. Yeah. See here. Question is the voltage regulation of an alternator. Voltage regulation of an alternator for 0.8, not 0.8. Voltage regulation of an alternator for 0.95 leading is 0. 95 leading is 0. Then the voltage regulation. For 0.9 leading. 0.9 leading. With other things remaining same. With other things remaining same. Remains the same. Will be A bit. A bit. Positive, B bit. Negative, C bit. 0, D bit. Data insufficient. Data. What is your answer? The voltage regulation alternator for 0.9 leading is 0. Then for 0.95 leading is 0. 0.9 leading is positive or negative? That's a question. Okay. What is your answer? This is our regulation curve. This is our regulation curve. Okay. Here it is 0.9 leading. For 0.9 leading, 95 leading, it is 0. 0.95 leading, regulation is 0. Okay. 0. But for 0.99 leading, you can take for this is 0.9 leading here. For 0.9 leading, definitely it will be negative. Negative. For this power factor, it will be always negative. So answer is negative. Negative side. Regulation is negative minus positive regulation. So it will be negative. Answer is negative. Left side. You are shifting left side means negative. If you shift right side, it is going to be positive. Okay. Positive. So we from this 0.9 leading. It is like this. Okay. Now, next question. If you are 0.98 leading, it is negative. If it is 0.99 leading is given, 0.99 leading means it is going to be positive. More than 0.95, you are reaching towards the UPF. Then regulation will be positive. Okay, less than 0.95, it will be negative. So next question. The voltage regulation of an alternator. Voltage regulation an alternator, voltage regulation of alternator, or for which of the following voltage, for which of the question is like this. Let me modify. For which of the following power factor, following leading power factor, for which of the following leading power factors voltage regulation may be positive. Voltage regulation may be positive. A bit. 0.8 leading, B bit. 0.5 leading, C bit. 0.98 leading, and D bit. D bit, ZPF leading. Tell me what is the answer for this. For which of the following leading power factor? For which of the following leading power factors voltage regulation may be positive? What is the range for which power factor? Power factor. Okay. What is the answer? Okay. You will get voltage regulation will be which following leading power factor regulation positive? 0.98 leading. Closer to zero regulation is closer to 1. Zero regulation is closer to 1. Positive will be still very closer to. From this diagram you observe here, I have drawn very clear. Zero itself, zero regulation is closer to 1. Positive means still very closer to 1. Very closer to 1. Very close, nearer to 1. Okay, right side you have to shift. Okay. Now, next question. See. Next question. The voltage regulation of an alternator. The voltage regulation of an alternator. Voltage regulation of an alternator for a 0.8 lagging power factor. 0.8 lagging power factor is 20%. The voltage regulation of alternator for 0.8 lagging power factor is 30%. 30%. Then the voltage regulation. For 0.8 leading power factors. 0.8 leading power factor. Okay. Other things remaining same. With other things same. With other things same. Will be. Other things means what? Current same. Current to speed to. Only power factor is different. With other things remaining same means current to speed everything. Current to speed everything. Will be same. Will be answer A bit. Less than 30%. B bit. More than 30%. C bit. Equal to 30%. D bit. None. The voltage regulation of an alternator for 0.8 lagging power factor is 30%. And the voltage regulation for 0.8 leading. What will be the regulation? It will be always less than compared with leading power factor, lagging power factor. Lagging power factor, leading power factor always regulation is less. See here. Listen. Another important point. Here curve is more steeper, dear students. Regulation curve is there. Regulation curve is more steeper for lagging power factor. Lagging power factor regulation is more. Leading power factor side regulation is less. Curve is steeper. Why I have drawn curve is steeper here? Because lagging side regulation is more. Reason is already we have seen. Two drops, resistance, reactance, both are causes drop. That's the reason regulation is more, curve is more steeper. But this side it is flatter. Even if you compare for 0.8 lagging power factor, this is for 0.8 lagging power factor, this is a regulation. This is a regulation for 0.8 lagging. 0.8 leading how much? Very less, na? Very less. Regulation is very less. Leading power factor regulation is more. Not only 0.8 leading, if you say even for 0.6 lagging, this much regulation, but for 0.6 leading, this much regulation. Regulation is less. Regulation is more for lagging power factor. Why? Because two drops already I have given. Right? Answer is less than 30%. Because regulation always more for, reason is regulation. Regulation is always more for lagging power factor. More for lagging power factor. Since both are the drops, both are the drops. Both means resistance and reactance. Both causes drop of voltage. That we know. Similarly, next question. Next question is, the voltage regulation of an alternator. The voltage regulation of an alternator is the voltage regulation of alternator for 0.8 lagging. 0.8 lagging power factor is 30%. 30%. Then the voltage regulation for 0.707 lagging. 0.707 lagging will be A bit. Less than 30%, B bit. More than 30%, C bit. Equal to 30%, D bit. None. But none. Okay? Yeah. What's your answer? The voltage regulation of an alternator for 0.8 lagging power factor is 30%. Then the voltage regulation for 0.707 lagging, how much? Second question? Yes. See. From this diagram, observe here 0.8 lagging, 0.6 lagging. Where is 0.707 will be? 0.707 will be in between this. It may be 0.707. What is that? Regulation is more compared with 0.8 lagging. Compared with 0.8 lagging, regulation is more. So regulation is more than 30%. Regulation is more. Not only, as power factor decreases, regulation is increasing. Answer is, your regulation will be more than 30%. More than 30%. Remember that. Voltage regulation. Armature reaction. Voltage regulation. First of all, magnetization or demagnetization. Armature reaction is inversely proportional to power factor. Armature reaction is inversely proportional to power factor. As power factor decreases, armature reaction increases. But the ZPF lagging is there, more demagnetization. Compared with 0.8 lagging, ZPF lagging is more demagnetization. So, voltage regulation is proportional to armature reaction. Voltage regulation is proportional to armature reaction, but that is inversely proportional to power factor. Power factor. Okay. So therefore, what is that? Voltage regulation is inversely proportional to power factor. As power factor decreases, regulation increases. You can observe on the diagram. Okay. Inversely proportional. Fine. Right. Yeah. The graph you see, inversely proportional. Power factor decreases, regulation is increases. As power factor decreases, 0.8, 0.4 like that, regulation increases. Even leading side also. Leading side also. Okay. Now, see next one. The voltage regulation. The voltage regulation of an alternator. Voltage regulation of an alternator for 0.8 lagging power factor. 0.8 lagging power factor is 12%. 12%. 12%. Then the voltage regulation. The voltage regulation for 0.8 leading. 0.8 leading with same current, the same armature current. Armature current will be A bit. It will be 0.8 leading, same armature current will be A bit. 12% B bit. Minus 12% C bit. 0% D bit. Minus 1.2%. Tell me, what is the answer for this? Voltage regulation of an alternator for 0.8 lagging power factor is 12%. Then the regulation for 0.8 leading, how much? 0.8 leading, is it less or more? Answer is, yeah, definitely for 0.8 lagging 12%, 12%. Therefore, it is not 12%. It is not 12%. No, not 12%. Not minus 12% also. Magnitude is never be equal. 0.8 leading, regulation always less, always less, always less. So either C or D, CD. But C also not possible. Why? Because 0.8 leading is not closer to UPF. Okay? Not closer. When you will get zero regulation, leading power factor closer to 1, closer to 1. But 0.8 leading is not closer to 1. This is correct answer. Not will be, sorry, you please make it with same armature current. Please change this with same armature current. Maybe the voltage regulation for 0.8 leading power factor with other things remaining same. Maybe. It's not will be. I cannot prove how it is minus 1.5. But among this, which option is correct means this is only correct. Minus 1.2 is appropriate answer. Similarly, yeah, see the voltage regulation. The voltage regulation is maximum for which of the following power factors voltage regulation will be maximum? For which of the following power factors voltage regulation is maximum. So 0.8 lagging B bit, 0.5 lagging CBIT. ZPF lagging, DBIT. ZPF leading. ZPF leading. Tell me for which power factor regulation is maximum. Definitely, maximum regulation is closer to 0 power factor lagging. But among this 0.8 is not closer to 0 and 0.5 also not closer to 0. ZPF lagging. So therefore ZPF lagging only correct. ZPF lagging only correct. No other power factors are closer to 0. If you take any problem, solve the problem, you will get maximum regulation for compared with this 0.8 lagging, 0.5 lagging, you will get maximum regulation for ZPF lagging only. If it is the other option is given 0.1 lagging, 0.2 lagging means now we will be in dilemma. But one more option also given 0.1, 0.2 lagging, we cannot answer because we don't know exactly. He never gives such type of questions. No two options are closer answers, he won't give. Okay. Now last question is very famous question, that is based on the speed. The question is, see, well-known question. The voltage regulation of an alternator, at 1000 RPM. 1000 RPM at 1000 RPM is 20%. 20%. Then the voltage regulation. At 900 RPM. 900 RPM with other things remaining same. Remains the same. Will be a bit less than 20%, B bit, more than 20%, C bit, equal to 20%, D bit, none. So what is your answer? Voltage regulation of an alternator at 1000 RPM is 20%. Then the regulation at 900 RPM with other things remaining same will be. Answer is, it is 20%. Voltage regulation is independent of speed. 20% only, 1000 RPM or 900 RPM, whatever it may be, 1200 RPM. Voltage regulation is independent of speed. Voltage regulation is independent of speed. Voltage regulation is independent of speed. Independent of speed. It depends on magnitude of the load and load power factor. Magnitude of load and load power factor. Does not depend on the speed. Independent of speed. Independent of speed. Okay. Reason is, let us see. Reason is regulation is equal to E minus V by V. Okay. That is equal to IA into ZS roughly. IA into ZS by V. That is nearly equal to IA into XCS by E. Roughly I am taking almost IA XCS by E. Okay. Yeah. Now here Xs is proportional to, Xs is equal to 2 pi FLS, 2 pi FLS. Therefore, Xs is proportional to frequency, Xs also proportional to speed, proportional to speed. Therefore, Xs is synchronous reactance is proportional to speed, number 1. Similarly, E is equal to, we know, 4.44 Kp Kd 5ft. Therefore, E also proportional to frequency, that also proportional to N. Therefore, E also proportional to N. Correct? Yes. E also proportional to N. Now, okay, E also proportional to N. Yeah. Then by taking this, see, from here, both are proportional. But whereas regulation is equal to IAXS. IAXS divided by V, IAXS divided by E. So as N decreases, XS decreasing and E also decreasing. Both numerator and denominators are decreasing. Both numerator and denominator, both are decreased. Therefore, regulation is constant. So what will happen? Both will be, regulation is equal to IA into XS by E. So both has reduced. This XS is reducing, E also reducing. Therefore, the regulation is constant. Regulation is constant. Regulation is independent of speed. Independent of speed. Okay. So these are the type of questions. I hope even any type of question is given also without data. Data is given, we can calculate, we can say answer. But when data is not given, so these are the common sense type of questions. Right? Now let us take the break for 20 minutes, then we will start. We are going to see the next topic. First we will do some problems and then break for 20 minutes. Therefore, class will start again. What time? 7:38 to 7:58. 7:38 means 7:58. Okay. Yeah. Are you ready? The announcement for you, tomorrow schedule. Tomorrow schedule is 6:30 a.m. to 8:30 a.m. synchronous machines. Synchronous machines. 6:30 to 8:30 a.m. synchronous machines tomorrow. That is on 26. 9/21. Okay. 6:30 to 8:30 a.m. synchronous machines. 9 a.m. to 1 p.m. Signals and systems. Signals and systems. Right? This is one announcement. Another one is exam date also. See, exam date. 4th October. 4th October. Okay. 4th October, your examination is subject to power electronics. Power electronics. Timings. Exam time. 4 p.m. to 4:45 p.m. Okay. Please note these points. Tomorrow your schedule 6:30 a.m. to 8:30 a.m. synchronous machines. Okay. Tomorrow morning 6:30 to 8:30 a.m. synchronous machines. 9 to, please make a note. 9 a.m. to 1 p.m. Signals and systems exam. Okay. Yeah. Now next, let us do one problems based on this. The problem is okay. Yeah. Okay. See, dear student, are you ready? Yes. Let us do one problem. The problem is sorry, 1 minute. Okay, just a minute. Yeah. See here. Dear students, the problem is, take down the problem. problem. On voltage regulation. See this problem. Problem 24 to 27. Problem number 24 to 27. The problem is given. It is a three-phase 415 volts 10 kVA star connected alternator has per phase impedance of 0.4 plus J5 ohms. 0.4 plus J5 ohms. First, 24th question, the power factor at which voltage regulation is zero. Power factor at which voltage regulation is zero. The options, 0.8 leading, 0.974 leading, 0.974 leading, lagging. Similarly, and other options, see, the other options, the power factor at which voltage regulation is maximum. Power factor at which voltage regulation is maximum. This is one question. And next, the maximum possible voltage regulation at rated condition is. Rated condition is. Next question, the voltage regulation at 0.8 power factor leading at half rated condition will be. Is a question. Okay. Yeah. So what is the page number? This is a question. I hope this has been circulated for you now. You will be having this booklet. In the booklet questions, whatever we have given. Okay. Yeah. Let us see this question. Okay. I'm having my own calculation because I cannot operate the calculator. We'll see. This is a question. The question is a three-phase alternator. A three-phase alternator. A three-phase 415 volts. A three-phase 415 volts. 10 kVA. 10 kVA star connected alternator. Correct? Star connected alternator has an impedance of how much? 0.4 plus J5 ohms per phase. 0.4 plus J5 ohm per phase. Under that, question number 1 is the power factor at which voltage regulation is zero. At which voltage regulation is zero. Okay. What are the options? 0.8 lagging, B bit. 0.8 leading, C bit. 0.974 leading, D bit say. 0.974 lagging. Second question, the power factor at which voltage regulation is maximum. Voltage regulation is maximum. That is A bit. 0.8 lagging, B bit. 0.08 lagging, C bit. ZPF lagging, and D bit. 0.1456 lagging. Third question, the maximum possible regulation. The maximum possible regulation at rated condition is dash. Fourth question, the voltage regulation at a half rated condition for 0.8 leading power factor. For 0.8 leading power factor is dash. This is the question. Once again, I'm writing. See, Okay, the data given a 3-phase 415 volts 10 kVA star current alternator. Power factor at which voltage regulation is 0. Power factor at which voltage regulation is maximum. Maximum possible regulation at rated condition. Voltage regulation at half rated condition. Now let us solve this question. Solution is, he has given the data a 3-phase 415 volts, no? 415 volts 10 kVA star connected alternator. So first you calculate. In the data given always it is line voltage, and phase voltage is equal to how much? 415 by root 3. So that is 239.6 volts. 239.6 volts. And IL is equal to kVA divided by root 3 into VL. Root 3 into VL. Correct? Yes. IL is equal to, I think you may be knowing, kVA is equal to root 3 VL IL cos phi, not cos phi. kVA is equal to what? Root 3 VL IL, or that is also equal to 3 VPH into IAPH. I think kW is equal to what? Root 3 VL IL cos phi, or that is also equal to 3 VPH and IAPH cos phi. Total kVA, total power. Okay, IL is equal to kVA divided by root 3 into VL. So unless otherwise mentioned, always you need to take in the data given line voltages. So 415 line voltages, 10 kVA is given. The 10 kVA is 10 kVA is rated kVA. So 10 divided by 10 into 10 power 3 divided by root 3 into VL. VL how much? 415. That is equal to divided by root 3. How much it is? 13.91 ampere. 13.91 ampere. That is also equal to phase current. Why? Because it is star connection. Line is equal to phase. Line current is equal to phase. So find everything per phase values in every equation. Important thing is any equation is there. Substitute everything in terms of per phase values. So cos theta plus phi is equal to minus Ia Zs divided by 2V. Because Zs will be given always per phase values. So all other things also must be per phase. That's the reason we are calculating per phase values and keeping ready. Okay. See, we have to find condition for zero regulation. First question. What is that first question? And at the same time, before that, calculate Zs. Zs is equal to how much? 0.4 plus J5 ohms. That is equal to 5.01 at an angle 85.42 degrees. That is. So under that, first question is the power factor at which voltage regulation is 0. Voltage regulation is 0. Solution is, we know that condition for zero regulation, cos of theta plus phi is equal to minus Ia Zs divided by 2V. Cos of theta plus phi is equal to minus Ia Zs divided by 2V. Therefore, cos theta how much? 85.42 plus phi. Cos theta plus phi is equal to minus Ia. Why Ia will be per phase? Why? Because Zs is per phase, na? Zs is per phase means Ia also must be per phase. Minus Ia. Ia is equal to how much? 13.91 into Zs. Zs is 5.01 divided by 2V. 2 into 239.6. You need to substitute every time per phase values only. That is equal to how much? And from this you calculate phi. From this calculate phi value. Phi is equal to 12.95 degrees, you will get 12.95 degrees. Therefore, then power factor is equal to cos phi, cos 12.95 degrees. Cos 12.95 degrees. That is equal to 0.974 leading. 0.974 leading. 0.974 leading. That is your answer. So answer is, what is your answer? Answer will be C. C earlier it is given C. Power factor at which voltage regulation is 0. Conditionally based numericals. Conditionally based questions. Yeah. Next question. See. What is the second question? Second question, power factor at which voltage regulation is maximum. Second question is given, power factor at which, question number 2, power factor at which voltage regulation is maximum. Voltage regulation is maximum. Okay, yes. And we know condition for maximum regulation. Condition for maximum regulation is phi is equal to theta. Phi is equal to theta. But theta how much? You got theta is equal to 85.42, no? 85.42 theta degrees. 85.42. Then what is the power factor? Power factor is equal to cos phi. Cos phi means cos 85.42. That is equal to 0.08 lagging. 0.08 lagging. This is your answer. Okay. Now, similarly, third question. Third question is maximum possible regulation. Maximum possible regulation. Maximum possible regulation at rated condition is, dash. Maximum possible regulation at rated condition is dash. How to do this problem? Maximum possible regulation at rated condition. See, regulation is depends upon two things, dear students. Regulation is depends upon the two things. What is that? One is current, another one is power factor. One current, another one is power factor. Current he has given rated condition. Rated condition means current is rated value 13.91. But for which power factor you will get maximum regulation? Maximum regulation is for power factor angle phi is equal to theta. So the maximum possible regulation, the maximum possible regulation at rated condition. At rated condition means IA, that is IA is equal to how much? Rated condition, IA is equal to 13.91 amperes. Rated condition will be for the power factor angle. For the power factor angle phi is equal to theta. Theta is equal to 85.42 degrees. 42 degrees. Okay. Maximum regulation at rated condition is asking, but which power factor it is possible? This power factor it is possible. These two things are important. For this power factor. So now calculate E value. For this condition, E is equal to square root of V cos phi plus IA RA whole square plus V sin phi plus IAXS whole square. It is lagging, na? Plus IAXS whole square. IAXS whole square. So substitute in this V cos phi. V is equal to 239.6 into cos phi. How much? Cos 85.42 plus RA square. Plus IA is equal to 13.91 into RA 0.4 whole square plus V sin phi. V is equal to 239.6 into sin 85.42 plus IAXS 13.91 into XS how much? 5 whole square. IAXS whole square is equal to, that value is how much? That is equal to 309.37 volts. 309.37 volts. Then regulation. This we know. Regulation is equal to what? E minus V by V into 100. Therefore, that regulation E is equal to 309.37 minus V. V is equal to 239.6 divided by 239.6 into 100. So that is equal to, what is your answer? Answer is 29.11 percentage. Okay. This is one type of problem. I am doing for each model. Four questions are different questions. Next question. Next one. Next question is regulation at half rated condition for 0.8 leading power factor. 0.8 leading. Fourth question is voltage regulation at voltage regulation for 0.8 leading at half rated condition. Voltage regulation at half rated condition. Half rated condition for 0.8 leading power factor. For 0.8 leading power factor is dash. So we have to calculate 0.8 leading. But that is half rated condition means what is the current? Half rated condition. Half rated condition means at half rated condition, IA is equal to half, 13.91 by 2. It is 6.95 amperes. 95 amperes. Therefore, you have to find half rated condition. This is the current and this is the power factor. For this power factor, we have to calculate. Okay. The current power factor is important. Now, substitute in the relation. We know the current E is equal to square root of V cos phi plus IARA whole square plus V sin phi minus IAXS whole square. Minus IAXS whole square. Why minus? Leading power factor. Leading is asking 0.8 leading. So substitute in this V. V should be taken always 239. 239.6. Okay. V. Or V also half. Some students will raise a doubt, silly doubt. Not silly doubt. Half rated condition, current to be taken half. Voltage to be always taken rated value only. Voltage. Load and current. So for example, in your house, 10 bulbs are there, 10 bulbs. But all bulbs are connected in parallel, na? All loads connected in parallel. But each bulb requires 230 volts. That is the rated voltage. Rated voltage. If you switch on all 10 lamps, say your current is rated. If you switch off half of the load, only half of the load, half of the bulbs are working. Then current is going to be half. But voltage is same, na? Yes. So while calculating the regulation, V to be taken always rated only. V must be fixed, rated to be taken, but current only changes. So it is 239.6, it is same. Cos phi means how much? 0.8 leading plus IA 6.95 into RA is equal to 0.4 whole square plus 239.6 into 0.6 minus IA 6.95 into excess is equal to 5 whole square. That is equal to how much? E is equal to, yeah, that E is equal to 222.92 volts, 92 volts. E. Then regulation, what is regulation? Regulation is equal to E minus V by V into 100. So E is equal to 222.92 minus 239.6 divided by 239.6 into 100. Therefore, your answer will be minus 6.96 percentage. Minus 6.96 percentage. Okay. So mainly there are two types of problems. So far we have covered. Remember that GATE examination is mainly problems, numericals. So we have to do minimum number of problems, but that should be covered all varieties of problems. I am doing only one problem that covers 4 varieties of problems now. Yes. In the examination, what he will give? If you want to give the problem, say, numericals may changes. Correct? Relations same, na? Equations are same, relations are same. As I told, there are 6 type of problems, 6 type. Among the 6 type of problems, one is EMF equation problem we are completed. Second type of problem is voltage regulation. Voltage regulation. And of course, is also asking regulation problems based on the synchronous impedance method that we are going to see tomorrow. Synchronous impedance method also is adding the concept of synchronous impedance. Fine. So now you are ready to do the problems. Main important thing for you people, what you have to do is practice the problems on EMF equation. You might be completed already. Now to do some problems based on the regulation. Okay. Some problems. For example, ESC students are there. This problem compulsory, it requires calculator, no? Yes. But ESC students, without calculator, they will give the problem. How it is, see. So for example, the problem is like this. This is a problem. Question is, see. You will give per unit values. An alternator, how simple the question is. An alternator operating at rated voltage, with rated armature current, with rated load, rated voltage with rated load, fine. And then V is equal to how much? RA is equal to 0, but excess is equal to 1 per unit. Rated load UPF. Then regulation is. Then the regulation is dash. This is only the data is given, say. Then what is the solution for this? Solution for this is rated condition. At rated condition, what is V? V is equal to 1 per unit. IA is equal to 1 per unit. Power factor is given. Then calculate E value how much? E is equal to, at UPF, na? Yes. V cos phi plus IRA whole square plus V sin phi plus IAXS whole square. UPF also use plus. that is equal to V. V is equal to 1 per unit. Cos phi how much? 1. This is 0. IRA 0. Why? Because RA 0 na? Yes. IA is equal to 1 per unit. Okay. RA 0 whole square. V sin phi. V means 1. Sin 0 how much it is? Sin 0 also 0 na? This is 0. Plus IA. IA is equal to 1. X is also 1 per unit. So what is that? Square root of, this is 1 square plus 1 square. How much? Root 2. Root 2 is equal to 1.414 per unit. Per unit. E is equal to, that is E. So what is the regulation? Then regulation is equal to E minus V by V into 100. So E is equal to 1.414 minus 1 divided by 1 into 100 is equal to how much? 41.4%, like that. Is it require any calculator? Doing problems in ESE examination, no need of any calculator for this. Mostly you will get per unit values. Even GATE examinations also per unit. For simple calculation, calculations will become simple. Okay? Yeah. So this is about the type of problems. Okay. Yeah. Now, so you practice the problems, few problems, 1 or 2 problems. Example problems are given sufficient, just for practice. Then next topic is, we are going to see the regulation methods. Regulation methods. But before regulation methods, there are 4 methods are there. Synchronous impedance method, MMF method, ZPF method, ASA method. But all these methods are required characteristics of alternator. They require characteristics of alternator. Graphical methods. Characteristics means they need OC, OCC, SCC, ZPFC. So before coming to the voltage regulation methods, first let us discuss about characteristics of alternators. Characteristics. In examinations also, these characteristics also important. The questions based on the characteristics also. ESE students, characteristics particularly, you will ask characteristics of alternator. Now let us see characteristics of alternators. Characteristics of alternators. The characteristics are, number 1, open circuit characteristics. Open circuit characteristics, that is OCC. Next, short circuit characteristics. Short circuit characteristics, that is SCC, SCC. Third one, zero power factor characteristics. Zero power factor. The ZPF characteristics, zero power factor characteristics. That's said to be ZPFC, zero power factor characteristics. Fourth one, load saturation characteristics. Load saturation characteristics. Fifth one is external load characteristics. External load characteristics. Sixth one is compounding characteristics. Compounding characteristics. Open circuit characteristics. short circuit characteristics, zero power factor characteristics, load saturation characteristics, external load characteristics, compounding characteristics. Yeah, before drawing that, you should know what is the characteristics indicate. First OCC, that OCC indicates E versus IF. E versus at open circuit voltage versus field current. Open circuit voltage versus field current, and speed is constant. Speed is constant. E versus IF, speed constant. SCC is short circuit current ISC versus field current. Short circuit current versus field current, speed is constant. Speed not necessarily constant also. If speed is constant, fine, otherwise also same. Zero power factor characteristics. For zero power factor characteristics, they are the V versus IF. V versus IF. IA is constant, and power factor is ZPF lagging. Speed also constant. Speed is constant. Similarly, load saturation characteristics. For load saturation characteristics, this is also same. V versus IF. V versus IF. IA constant. Power factor also constant. Speed also constant. Speed also constant. IA constant, power factor constant, speed also constant. And external load characteristics. In external load characteristics, it is the V versus IA. V versus IA, where IF is constant, other things are constant. This versus this means whatever remaining things are, it is assumed to be constant. That is the meaning of definition of characteristics. So V versus IA. IF is constant, power factor is constant, speed also constant. Speed also constant. Compounding characteristics. Compounding, they are IF versus IA. IF versus IA. V is constant, power factor is constant, speed is constant. Speed is constant. Okay? Yeah. Fine. Now, let us discuss one by one. Okay. Yeah. So, in this session, we are going to discuss some characteristics and it will be continued for the next class. So, let us see now. First characteristics is open circuit characteristics. Let us see OCC. First OCC. Open circuit characteristics. OCC. Open circuit characteristics, it is E versus IF. Open circuit voltage versus field current, where speed is constant. N is constant. Constant. So to draw this, alternator will be open circuited. Measure the open circuit voltage. How you can measure? By connecting a voltmeter. If you connect a voltmeter across this, that will measure your open circuit voltage. That is E. It measures E. Speed is kept constant. It is rotating at its constant speed. Any constant only. This is IF and this measures E. Voltmeter measures E. And we know that E is equal to 4.44 Kp Kd phi ft, the EMF equation. E is equal to 4.44 Kp Kd phi ft. Kp constant, Kd constant, flux varying because we are varying the field current. E versus If na? Yes. Frequency constant, T constant. Why frequency constant? Speed constant. Therefore, in this, E is proportional to only flux. Other things are constant, proportional to flux. But flux is proportional to field current. Therefore, E is proportional to If. E is proportional to If. Therefore, E versus If, it will be linear. E versus If will be linear. Linear before saturation. If there is no saturation, it will be linear. Before saturation. And it will be non-linear after saturation. Non-linear after saturation. Non-linear after saturation. Because as field is keep on increases, field poles will tend to saturate. Therefore, non-linearity will come into picture. Now, based on this, draw the characteristics OCC. This is field current, E, open circuit voltage. The characteristics will be linear up to here, knee point, that is we are going to call. From there onwards, it is going to be non-linear. This is OCC, open circuit characteristics. This is said to be knee point, where saturation begins. Knee point, saturation begins. That is the knee. From there onwards, it will be non-linearity starts. Okay. Yeah. But of course, strictly speaking, even field current is zero, there is some voltage that is due to residual magnetism. And this will be the curve is actually like this. Curve is, but we can neglect the residual magnetism. Dear students, residual magnetism is not that much important for our alternator. Very much important for self-excited generators. Self-excited, shunt generator, series generator, they are important. Because the condition for build-up of voltage, residual magnetism is must. Residual magnetism is must there. But here, can you tell me one thing? Is the generator, alternator is it separately excited or self-excited generator? Is it separately or self-excited? Separately exciting. We are separately exciting. So no need of any residual magnetism. If it is there, fine. Normally, all field poles consist of some flux. Even field current is zero. That is due to retentivity property. They retain some flux. Even field current is zero. Okay. But synchronous machine is not that much important. Therefore, from here onwards, I will draw the graph curve from origin onwards only. Okay. Yeah. And if you draw the tangent to this, if you draw the tangent to this is said to be ideal OCC. That is called air gap line. Ideal OCC. That is also called air gap line. Whereas this is practical OCC. Ideal OCC means no saturation. If there is no saturation, it would be like that. If there is no saturation, we can expect it is linear, totally linear, if there is no saturation. But due to saturation, non-linearity will come into picture. Okay. This is about OCC. Next is SCC. SCC. After SCC, short circuit characteristics. This is important points we'll get. SCC. Short circuit. After the short circuit characteristics, and we can close our session. SCC, short circuit characteristics. What is short circuit characteristics? They are the ISC versus short circuit characteristics. That's right. Short circuit characteristics. SCC. The SCC is short circuit current versus field current. Short circuit current versus field current. Short circuit versus field current. This alternator it is short circuited with an ammeter. Short circuited an ammeter. Field current is measured with another ammeter. Okay. Yeah. So this is the field current. This is ISC. It measures ISC. ISC. Okay. Taken. Short circuit characteristics. Yeah. It is producing the flux, na? Yes, it is producing the flux, and when it is driven, an EMF will be induced in this. EMF will be generated. What that EMF will do? It will maintain the current. It will maintain the short circuit current. Short circuit current, but short circuit current also ammeter IA only. ISC is nothing but IA. Current under short circuit condition. It is circulating the current. Okay. Yes. So this important point here, ISC is there, na? That ISC will be lags E by 90 degrees. ISC lags E by 90 degrees. If you draw the phasor, this is phi m, main field flux is along D axis. Main field flux along D axis, and induced EMF will be along the Q axis. This is induced EMF will be always along Q axis, quadrature axis. Then current will be in this direction. This is ISC. ISC is itself IA. No, that is ISC. So ISC lags this E by 90 degrees. ISC lags the current by 90 degrees. Why? Why? Because the current circulate in the armature winding. Current circulate in the armature winding. So armature winding resistance is negligibly small. If you neglect resistance, it acts like a pure inductive circuit. No? Winding is itself pure inductive. So current lags the voltage by 90 degrees. 90 degrees. Then power factor, what is the power factor under short circuit condition? Power factor under short circuit condition is ZPF lagging. ZPF lagging. Okay? Yeah. See? A minute. Okay. This is E now? Yes, this is E. E will be along the quadrature axis. Quadrature axis. See, ISC. In this, ISC lags. ISC lags the E by 90 degrees. ISC lags the E by 90 degrees. 1 minute. Yeah. ISC lags the E by 90 degrees. 90 degrees. Therefore, power factor under short circuit condition. Power factor under short circuit condition is ZPF lagging. Is ZPF lagging. ZPF lagging. Almost ZPF lagging. Strictly speaking, power factor under short circuit condition is almost ZPF lagging. Almost ZPF lagging. Why? Because winding is pure inductive circuit, na? Yes, almost ZPF lagging. Strictly speaking, it is lags with an angle theta. Armature reaction is ZPF lagging means what is armature reaction? Armature reaction is purely demagnetization. Under short circuit condition, armature reaction is purely demagnetization. Okay, yes. Other questions, you know, these are itself questions. These are itself questions. What is the power factor under short circuit condition? ZPF lagging, ZPF leading, UPF. It is a ZPF lagging. Armature reaction is purely demagnetization. And I will ask one question for you. Tell me, under short circuit condition, the short circuit current is along the D axis or Q axis? Under short circuit condition, short circuit current is along the D axis. D axis. For ZPF leading also it will be D axis. It is lagging. Even ZPF leading also D axis. Unity power factor it will be along the Q axis. UPF it is Q axis. Strictly speaking, see, E is equal to, what is there? E is equal to, our equation, E is equal to V plus IA into ZS, IA into ZS. Okay? E is equal to V plus IA into ZS. But under short circuit condition, under SC condition, V is equal to 0, V is equal to 0, and IA is equal to ISC. IA is equal to ISC. Then what is that E? E is equal to ISC into ZS. ISC into ZS. Okay? That is equal to what? ISC into ZS. ZS is equal to RA plus JXS. IS into RA plus JXES. E is equal to. Okay. Now where that generated EMF is going? Where it is going? It is going only just to meet the synchronous impedance ISC into ZS. Okay. Yeah. Now what is ISC? ISC is equal to short circuit current. From this also equal to ISC is equal to how much? E by ZS. E by ZS. Short circuit current also equal to E by ZS. E by ZS. Now if you draw the under short circuit condition, to draw the phasor diagram, how it will be? That is a question in your previous ISC examination, IES examination question. See, this is phi m. This is phi m. V 0. V will be 0. What is this? This is going to be E. E. But V 0. IA. IA lags, na? IA lags. IA 90 degrees roughly. Practically it is theta. RA neglected, it is 0. But when RA taken, it is not 0. IA. Okay. If RA is not equal to 0, that is ZS, na? Yes. This I will write first. E is equal to what is that? ISC into RA plus JXES. 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 So this is IA. V0. V0 kabatti this is IA. IA is This is IARA, IARA, ISCRA, ISCRA. This is itself IS into XS. What is this? This is E. This is E. E is itself IAZS. That E. E is equal to ISC into ZS. This is a phasor diagram under short circuit condition. Phasor diagram under short circuit condition, it is like this. Phasor diagram will be like this. Under short circuit condition, it's a phasor diagram. Phasor diagram. Okay. It's a phasor diagram under short circuit condition. This is equal to how much? This will be theta. This is equal. This is theta. Theta nearly 90 degrees, no? Okay. Yeah. And you note down the coming to, if you draw the SEC, what to do? Take the readings, increase the field current, and note down the short circuit current. Then draw the graph. Draw the graph. See. To draw this, note down the readings. ISC and IF versus ISC will be taken. A set of readings will be taken. Then draw the graph. So if you draw the SEC, how it is going to be? This is SEC, IF and ISC. ISC. So SEC, this is SEC. SEC. Short circuit characteristics. SEC is linear. SEC is linear. SEC is linear. This is SEC. SEC is linear. There is no saturation. SEC is linear. SEC is linear. Short circuit characters are linear, but open circuit characters are non-linear. SEC will be always linear. Linear. Why reason? Reason. Why SEC is linear? Reason is no saturation. Simply to say no saturation. Why there is no saturation? Because of demagnetizing effect of armature reaction. Demagnetizing effect of armature reaction. Under short circuit condition, power factor is ZPF lagging. Power factor is ZPF lagging. Therefore, machine works at low flux density condition. Armature reaction is purely demagnetization. Under short circuit condition, see, when you are increasing the main field flux, simultaneously the armature flux also increases in reverse direction. Armature flux also increases in reverse direction. Demagnetization. Due to the demagnetization, machine works at low flux density condition. Machine works at low flux density condition, so there is no saturation. Hence, SEC will be linear. It is linear. So, reason is C. Yeah. Under short circuit condition, the power factor is under short circuit condition, the power factor is ZPF lagging. Power factor is ZPF lagging. And the armature reaction is purely demagnetization. Armature reaction is purely demagnetization. Purely demagnetization. Therefore, the machine works The machine works at low flux density condition. The machine works at a low flux density condition. Low flux density condition. Therefore, no saturation. Low flux density condition, no saturation. No saturation means hence SEC will be linear. Together, no saturation. Linear. Linear. Therefore, to draw the SEC, only one reading is enough. One reading. You take one reading and then join from origin, extend from origin. Okay? SEC will be linear. Even how much field current you increase, it will be linear. Why? Because when you are increasing the field current, armature flux also increases in opposite direction. Opposite direction. The machine works at low flux density condition. That's the reason iron losses will be neglected. Iron losses will be neglected under no load condition. Iron losses will be neglected. Neglected under short circuit condition. Under short circuit condition. Why? Under short circuit condition. Because low flux density condition. V maximum is low. V max is low. Is very less. V maximum is very less. Fine? Yeah. Now, then I will give two questions on this. They are the very common questions. In short circuit characteristics, the questions are very common. Let me give those questions. The short circuit current of an alternator. Question is, the short circuit current of an alternator. The short circuit current of an alternator at 1000 RPM. 1000 RPM is 20 amperes. Short circuit current at an alternator 1000 RPM 20 amperes. Then the short circuit current. The short circuit current at 900 RPM is 900 RPM with same excitation. With same excitation will be A bit less than 20 amperes, B bit more than 20 amperes, C bit equal to 20 amperes, D bit none. Short circuit current of an alternator. Short circuit current of an alternator is independent of speed. Answer will be this only, 20 amperes only. Short circuit current is independent of speed. It depends upon only excitation. Short circuit current is independent of speed. Independent of speed. It depends on excitation. Depends on excitation. Excitation. That is proportional to excitation. It depends on the excitation. That is field current. Field current. That is proportional to excitation. Proportional to excitation. Okay? Yes. Mean to say, see, here short circuit current independent of speed. By reason, let us see. Reason is E is equal to, we know, E is equal to V plus IA. And what is the short circuit current? I have given already. Short circuit current is equal to ISC is equal to E by ZS. That is nearly equal to E by XCS. E by XCS. Okay. Yes. But E is proportional to, already we have seen, na? Yes. E is proportional to speed and XS also proportional to speed. XS also proportional to speed. Therefore, as N decreases, E decreases as well as XS also decreases. XS also decreases. Therefore, speed is constant. Therefore, ISC is equal to E by XCS. E by XCS means both reduce, na? E decrease as well as XS decreases. Therefore, what is that? That is equal to constant. ISC is constant. ISC is constant. Those who are seeing this question very first time, they will go for less than 20 amperes. Correct? Yes. They will go for less than 20. Their thinking is like that. Yes. When speed is decreased, E also reduce. E reduce, therefore current reduce. Correct? E reduce. At the same time, XS also will reduce. That's the reason numerator and denominator both reduces. Therefore, ISC will be constant. If you draw the variation of speed, this is variation of ISC with respect to speed. If you draw, this is speed, say, and ISC, how it will be, characteristics. These are like this. Current is constant. This is SCC. ISC, independent of speed. It is independent of speed. Constant. Okay. ISC, variation of ISC with respect to speed, constant. Right? Some student will raise a doubt. Sir, it is not constant. We are feeling it is non-linear at the beginning. Yes, non-linear only. If 1000 RPM, if you take 900 RPM, 800 RPM, 1100, 1200 RPM, fine. But it will start from origin onwards only. Origin. Why? Because this conclusion is independent of speed, okay. But when speed is zero, what is the current? Tell me. When speed is zero, what is the short circuit current? Zero only. When alternator speed is zero means it is not rotating. When it is not rotating, it is not cutting any flux, no EMF, no current. Though it is short circuited, when speed is zero, where is the EMF? No EMF. There is no short circuit current. That's the reason it will start anyhow from origin. Okay. Yeah. Let us see lastly. The short circuit current of an alternator. The short circuit current of an alternator. Last question. Of an alternator is 20 amperes. 20 amperes. Okay. 20 amperes. Then the short circuit currented. Then the short circuit currented. The short circuit current at the short circuit current of an alternator at 1000 RPM. 1000 RPM is 20 amperes. 20 amperes. Then the short circuit current at 900 RPM. 900 RPM with 150% excitation is. 150% excitation is. 150% excitation is A bit. Less than 20 amperes, B bit. More than 20 amperes, C bit. Equal to 20 amperes, D bit. Equal to 30 amperes. Equal to 30 amperes. What is the answer? 30 amperes. Here speed does not matter. Speed may be 1000 or 900. It does not depends on the speed. But excitation has been increased to 150%. ISC. ISC is proportional to excitation. What is that excitation? Field current, na? Yes, field current. Does not depends on the speed, only excitation. Therefore, what will happen? Current ISC is equal to 1.5 times into 20 amperes. How much? It will be 30 amperes. Answer will be 30 amperes. Excitation is 150% means earlier the current is 20 amperes, but when excitation is 150%, current will be 30 amperes. Double 150%. Similarly, if current is excitation is 200%, doubled, say current also going to be doubled. Fine. So this is about so we are completed the for today topic, and next we are going to complete other remaining characteristics. Tomorrow we are going to see very important topic is synchronous impedance method. GATE examination most of the times is asking problems on synchronous impedance method. That we are going to do tomorrow. Okay. Yeah. Now any doubts? See, let us. Yeah. Hand raise. I am unmuting you people. Okay, you please carry on. Hello.
Hello.
Hello. Tell
Good
me.
evening, sir.
Good evening.
Sir, that doubt is, sir. Sir, that angle psi, when we are drawing the phasor diagram, you said a point that flux of phi A and that is phi R is del angle, na? And E and V is del also.
That is also same.
Okay, but when I am drawing hole, that is ER and phi R, that will be 90 degree, na?
ER?
ER, that is air gap, EMF, and phi R.
Phi R, 91, correct.
Then this is not satisfying, means it is not equally del shifted, because del is shifted between E and V, but that will be phi R and phi M, that angle is del.
Yeah. Yes, I will explain. Very good. Okay. See. Your doubt is based on the phasor diagram. No? Phasor diagram. This is phi M. Okay. This is E. V. IA. And IARA. This is IAXL. Of course, this is E. Right. IARA. This is IAXL. IAXA. Okay. Now, ER is nothing but IARA, IAXL. That is said to be ER.
Yes.
This is ER. ER is it? Okay. This is IAZS. ER will be this. This is ER. Right? ER. Now, so we have drawn. This is IA and this is phi A or FEA, you can say. Phi A. This is FEM or FEAC. FM and FA. First, let me take with MMA phasors. You are asking about MMA phasors, na? Yes. See, this is FM or phi M. This is FA or phi A. Phi A. And resultant, this is air gap. Air gap is equal to, this is phi R. Phi R. Phi R or FR. This is nothing but phi R or FR. Yeah. So here angle between what we have taken, angle between E and V taken as delta. Okay. Delta. And angle between V and IA, that is phi. Phi. Right. Angle between this side, this is 90 degrees. And this side, this also 90 degrees. Both are 90. Why? Because ER lags phi R by 90, E lags phi by 90 degrees. Now your doubt may be, this is delta. Yes, this we have given during our torque production. Tell me, when angle between phi FR and FM is delta, what is angle between E and ER is delta. Correct?
Yes.
Because 2 MMFs angle 90 degree delta means 2 EMF will be, definitely it will be delta. Strictly speaking, delta is the angle between E and ER. But ER cannot be measurable, and the approximation, that to be, this drop is there, na?
Yes.
This drop due to IA, RE, IAXL, it is very, very less, negligible. And angle between ER and V is almost zero.
Okay.
Zero. So that's the reason it will be approximated to, instead of taking ER, E and V will be taken.
Okay.
That approximation can be considerable. It's not much. You check the Nagaratan Kothari textbook, he has given very, very clearly. By neglecting IA, RE, IAXL, ER is equal to same, na?
Yes.
If ER is equal to, what is that? ER is equal to V plus
V plus
IA
IA
plus J into IAXL.
IAXL.
Fine, yes. If this is negligible, this is very, very small. Very, very small. Therefore, ER is equal to V. ER is equal to V. Now I can say, then what is the angle between ER is equal to V means angle is also same. In other words, delta is the angle between. Delta is the angle between, strictly speaking, FEM and FR. And the delta is the angle between E and ER, strictly speaking, E and ER. But that is approximately equal to delta angle between E and V.
Yes, sir.
That is only. Approximation. It is approximation can be taken. Okay. Hello, next.
Sir, sir, what is regulation formula? For transformer, we are taking no load voltage in denominator, sir. For alternator, we are taking terminal voltage.
Yes, correct. V.
What is the reason, sir? Once again.
Then I told na, in transformer, if you give V means when you are writing V on transformer nameplate details, whether he is giving E value or V value in transformer.
E value, sir.
Why E given?
Induced EMF only.
If load is connected, V will change. E always fixed no load voltage. V will change. As load connected, V is not constant. To lagging power factor, your V different, leading power factor, your V different. But E's are same. Then there is no possibility of controlling any terminal voltage. Transformer, you cannot control any terminal voltage. Therefore, V varies. That's the reason you cannot give V value or nameplate details. Because if V is equal to, if I give 230 volts means V cannot be maintained. Load changes, V may vary. But that's the reason E will be given. Whereas in alternator, terminal voltage will be given. On the nameplate details, V. 400 volts means that is V. And is it possible to maintain V value in alternator? Yes. 400 volts means off load condition also I will maintain 400. Full load also I will maintain 400. Lagging power factor also I can maintain 400. Leading also. How it is possible? By excitation, by changing the excitation. So V will be given. V
Even
is
if
the-
load is changing, terminal voltage will change, but for due to excitation, we will maintain constant.
Yes, yes, you can maintain. V, once you are writing on the nameplate details means that has to be maintained. It is possible in alternator, not possible in transformer. That's the reason E will be taken as reference. E fixed always. In alternator, V can be maintained the same, and according to that V, I will generate more voltage. E can be variable. Ante kada. Whenever if you want 0.8 lagging, E may be more, E may be less. That E I can change. Why? Excitation. Based on that, V can be maintained. More drop is there, say I can generate more voltage. Less drop is there, say I can generate less voltage, so that rated voltage can be maintained. That's the reason we will be taken. See, only transformer only in the denominator E will be taken. Now all other machines, you take DC generator or transmission line, whatever it may be, it will be V will be taken. Okay. Next.
Hello, sir.
Hello. Tell me. Hello.
Sir, what is the effect of cross magnetization, sir? What is effect of cross magnetization?
Cross magnetization is distort. It will develop the torque actually. Cross magnetization means mainly, of course, anyhow, it will causes a bit drop, no doubt. Rather than the drop, its effect, cross magnetization means it distort the flux. For example, see, this is one conductor, this is a flux. I think DC machines, are you completed?
No, sir.
At leading pole tip, trailing pole tip. At leading pole tip, trailing pole tip. Leading pole tip, armature flux aids one side of the flux, other side it will be opposes. So this is the flux, say for example, this is the flux. The flux. We take one conductor. This is a conductor, no? Cross, say cross. Cross means what is the flux lines? Armature flux lines. They are clockwise direction. Okay.
Yes.
Clockwise direction. Clockwise direction. Now at the top of the conductor, what is happening? Both fluxes are aiding, na?
Yes, sir. Crowded.
At bottom of the conductor, both are opposing. Therefore, more flux lines takes place here. Flux lines are more, but less flux lines. Due to that, torque will be developed, force. Cross magnetization causes cross. And flux uneven. Flux at the one side of the conductor increases, other side of the conductor changes. And in the air gap, flux distorted. Flux distorted. That is called cross magnetization.
And it will lead to torque formation.
Huh? Yeah.
And further
It will produce as a torque. Yes.
Okay.
If UPF you take, UPF unity power factor, it will mainly torque is more.
Sir, one more
Also,
question that our another question, sir.
100?
That double. Sir, another question I want to ask, sir.
Tell me.
That double layer winding I have sent you on WhatsApp, sir.
Okay. I will draw the diagram. You have kept your message for me.
Yes, sir.
Another student also there. What I will do? I will draw the diagram. Okay, I will send it to you. Actually, night itself I have drawn. One more student also asked.
I was only that, sir.
Okay. You only asked, huh?
Yes, sir.
Yeah. Can you stay for some more time?
Yes, sir. Definitely.
Okay, let me attend other people. Any other people are there? Hello?
Hello, sir.
Tell me.
Sir, please open once problems, sir.
Problem, huh?
It's a regulation problems.
Okay. Tell me in this.
When speed changes 1000 RPM to the 900 RPM problem, sir.
Okay.
Sir, what I have think like that when the speed decrease, the IMF inducer will be
Yes, correct.
reduced, sir. So like that.
That is only it will not, E decreases, excess also decreases, reactance. Alternator current circulate in the winding, na?
Yes, sir.
Is circulating here. Okay? E is there. And it is circulating current. So E decreases, reactance also. Reactance of the winding also will reduce.
Okay, sir.
Excess is also proportional to speed.
Okay, sir.
It will also reduce. Okay?
Then it will remain same, sir.
Remain same. That is a standard question. IS is equal to E by ZS, E by XS. So speed reduces, E decreases, XS also decreases. Both are proportional to speed. Both will reduce with the same percentage. Same percentage.
Okay, sir.
As a fixed. Hello? Hello?
Hello, sir.
Ah.
Okay, sir. Understood. It will always remain same, sir. What
Yes,
about the speed means large deviation also?
Whatever it may be. Correct. It will be same.
It means XS means XA plus XL also both. Okay.
XL also both. XL is equal to 2 pi FL, kada?
Sir.
XL is equal to 2 pi FLS.
Okay, sir.
That is also proportional.
Sir, impedance angle means any other definition, sir? Means explain one.
Theta. Impedance angle means winding impedance angle. Theta is equal to tan inverse of XS by RA.
So, sector theta is equal to load power factor. Phi is equal to impedance angle. Sir.
Phi load power factor angle. Phi is the load angle. Load power factor means if you take RL load, phi is equal to tan inverse of XL by RL. If resistive phi may variable. For example, if you take pure resistive load, what is phi? Phi will be 0.
Okay, sir. But if we R plus JX means whenever X term will be there, angle will be.
Theta fixed. Theta is equal to tan inverse of XES by RA. What is that XS? Winding impedance, winding reactance. So RA winding resistance. Winding resistance reactance, they are not going to change. They are always fixed.
Okay, sir.
But load side is there, na? It is variable. RL load means X by R ratio may be different. It may be 0.8 lagging, 0.8. 5 value may vary.
5 means load side, sir.
Load side and 5.
Load side power factor. Theta means angle between V and IA.
Machine side.
V versus IA. V to the IA.
Then ki
According to the phasor diagram, sir.
V into IA angle is load side, load power factor angle.
Okay, sir.
Theta is the angle between. Theta is not angle between E and I. Impedance angle. Only impedance.
At that angle theta, sir.
Theta is a tan inverse of XES by RA.
XS by RA. Okay, sir. Means Z at an angle theta will.
There is a theta.
Okay, thank you.
Okay, right. Yes. Hello. Hello, Shravan Kumar.
Yes, sir. Okay, sir. Clarified. Thank you, sir.
Okay, right. Next, anybody? Hello.
Hello, sir.
Sir,
these common data problem, sir. Common data problem.
Common data problem.
Sir, in this 24th question, and first question, sir, we have find out the power factor, no, sir? 0.974.
Yes.
First one. Sir, how we know that is leading or lagging power factor?
Okay, very good. But this zero power factor, zero regulation you will get for leading power factor, lagging power factor.
Okay. Sir?
Zero regulation we have done, ma. Zero
Yes, sir.
is asking at what power factor regulation is zero. Zero regulation for leading power factor you will get lagging power factor.
Yes.
Leading ye kada.
Yes, sir.
The derivation is for leading.
Okay.
Right. Hello.
Sir, PDF will be uploaded after 1 hour, sir.
Yeah, now itself I will upload. I will send to the Seshu and he will upload.
Okay, sir.
Yesterday I uploaded. I send after completion of the class. I also give the message. We will
Okay.
upload now itself. Huh?
Okay, sir.
Okay. Yeah. Next, fine. Are you there? The double air winding. Hello.
Yes, sir. Yes, sir.
What is your name? Double air. Navdeep.
Navdeep, sir. Yes, sir.
Okay, Navdeep. Yeah, let me do. I will use clock diagram. Okay. Where you have 18 slots. Slot alternator. For this, what is slot angle? You will get gamma. Slots per pole per phase
20 degrees.
3. SPP 3. M3. Gamma is equal to 20 degrees. Gamma P into 180 by S. P is equal to 2. 180 by 18. That is equal to how much? 20 degrees. Gamma 20. Okay. So for this, see. Okay. I am taking directly stator. Dividing that into 3 parts. Now I will divide into 6 parts. Okay.
Yes, sir.
And inside of that again, each part 3 slots will be there. No? Yes. Yes. Now, see, this is slot 1, slot 1, slot 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 slots total. Okay? Yeah.
Yes, sir.
Now let us, the top one is top layer, bottom one is bottom layer. Okay? Now let us keep the winding. See, first R phase I will start where full pitch winding. First let me draw for full pitch winding. Okay, after that I will come to the short pitch for full pitch winding. Full pitch winding where R can be kept first slot. R1, R2, R3. Okay? R1, R2, R3. Where other side?
10, 11, 12.
10, 11, 12. Bottom layer, but that will be under bottom layer means here. This is bottom. R1 dash, R2 dash. No, sorry. 10, 11, 12.
R1
R1 dash, R2 dash, R3 dash. Right. Next, y1. Where y1? 7.
7, 8, 9.
y1, y2, y3.
Right.
Other side will be 16, 17, 18. No?
17, 18.
y1 dash, y2 dash, y3 dash.
In lower side.
16, 17, 18. y1 dash, y. Huh?
In lower layer it will be there.
Correct. You are right. Lower. y1 dash, y2 dash, y3 dash. Okay. Then where B must be kept again another 120 degrees apart. 7 to 13, no?
13. Yes, sir.
B1, B2, B3. Other side will be in bottom layer of 4-1. B1,
4, 5, 6.
B2, B1 dash, B2 dash, B3 dash. Okay? Now one set of finding is completed, na?
Yes, sir.
One set of finding is completed. R phase, Y phase, B phase. Okay?
Yes.
First, what we have done? R to Y we have done. Y to B completed. Okay?
Yes, sir.
Now here, one layer of winding is completed. Half of the winding is completed. Now, again, where to start? If you want to start again from B, immediately where B is started, na? Where B is started, this is B is there, na? To start with R phase there again. And B immediately completed R phase. But that you have to wound in counterclockwise, reverse direction. Here immediately R I will start here. See, B1 dash, B2 dash, B3 dash is completed here. There immediately what you have to do is, now I will go in counterclockwise direction. I can keep R4, R5, R6 in this slot. In this slot. Now let me go in reverse direction, counterclockwise.
It is not 120 degrees, sir.
180 degrees.
It should be 120 degrees from B phase.
Correct only. Where? It will come automatically.
Sir, it should be from B1, sir. R4.
B1 only.
How, sir?
R4 dash. No, it is not from B1. R, Y, B is there, na?
Yes, sir.
R1, Y1, B1, I completed.
Yes, sir.
Okay. Now reverse I will come reverse. R4, R5, R6. Let me complete first. R4, R5, R6. Okay. And where to keep other side? Counterclockwise. I am coming counterclockwise. 180 degrees. Where to keep?
12th, 11th, 10th.
That is from in counterclockwise direction. It is nothing but how much it is? 20, 40, 60, 80, 100, 120, 140, 160, 180. 180 means I need to keep here. Where is that? This is R4 dash, R5 dash, R6 dash. Okay?
Yes, sir.
Next, where to keep that B, Y? No. R is there now. After R, you are coming counterclockwise direction. Counterclockwise direction, again you have to come for B. After R 120 degrees, you need to keep B counterclockwise. I am going now.
Okay. Yes, sir.
If you go clockwise, R, Y, B. Now I am starting again immediately. After completion, immediately at the completion of B phase, I will again start with R, but in counterclockwise direction. This is clockwise. After R, which will come? B will come. RBY. Reverse direction, you have to come. Clockwise winding, counterclockwise. Tell me where it will come. R4 to B4, you have to keep 120. R4 to B4.
15th, sir.
R4.
15th, 14th.
From here, 20, 40, 60, 80, 100, 120. 120 means B4 will come here.
Yes, sir.
B4, B5, B6. Okay. You have to start here. Now angle you can find same thing. Then where other side can be kept? 180
It's
degrees.
4, 5,
180
6.
degrees is where it will come? 4, 5,
4,
6.
5, 6.
4, 5, 6. From B4. 20, 40, 60, 80, 100, 120, 140, 160, 180. Yeah, this is B4 dash, B5 dash, B6 dash. Right?
Yes.
Next Y, B to Y, B to Y 120. B is there, B4 to Y4 120. 30, 60, 90, 120, sorry. 20, 40, 60, 80, 100, 120. And Y will start here, na? Y4, Y5, Y6. Then reverse 20, 40, 60, 80, 100, 120, 140, 160, 180. No. Counterclockwise. Where is I am here now? Y4, correct. 20, 40, 60, 80, 100, 120, 140, 160, 180. Yes. Y4 dash, Y5 dash, Y6 dash. This is the winding for full pitch.
Yes, sir.
Now both top and bottom were occupied with same phases.
Yes, sir. Sir, but in class you said that R4 or 5 and 6 would be also 120 from B phase. In class you said that second layer should be 120 degree from B phase.
I cannot draw this total diagram there. No? My intention is there only bottom layer shifted left side. Here also I can show bottom layer shifted left side. Okay. But you can check in this diagram anywhere you will get angle between R by B 120 degrees will be maintained.
Yes, sir, that is there. Sir, I'm
is
asking, sir, that when we are placing second layer, sir,
second layer only.
at that time we have to check that condition that it should be 120 degree.
No. R to Y 120, Y to B. It is not like that. Now in this diagram you check it. It's very on that day I have told R1 to Y1, Y1 to B1. That is okay.
Yes, sir.
If I draw whole thing, finally what you need, bottom layer will be shifted. That's the reason I just shown only ninth slot it can be kept. Okay, ninth slot it can be kept. Full pitch winding, it is valid. Whatever I told full pitch winding, the same diagram you are getting, na?
Yes, sir.
Same
But that-
diagram you will get.
But that R4 and R56 were in 1, 2, 3 slot. In reverse way order they were.
That is okay. But placement is same, na?
Yes, sir.
Placement is same. There I cannot explain. Full pitch winding, it is valid. But short pitch winding, this is correct thing. This is whatever I am drawing. Practically, we will do like this only. Now, if you draw for short pitch, same way. Let me draw with short pitch winding. You can observe the same thing also. In this, both top and bottom layers are occupied with same phases. Okay. In this top bottom layers, in all the slots, they will be occupied with same phases or not?
Yes,
You take any phases, same phases they are occupied. Here. You can take this slot occupied with same phases. These slots. They are occupied with same phases. Top layer, bottom layers. Same phases. Okay? And even R1, R2, R3, you can find top and bottom layers occupied with same phases. Now, let me draw for short pitch winding. Now, you are having idea, na? Let me draw this. Short pitch winding, if you take short pitch winding now. Okay. Yeah. Right? Now we again divide into 3 parts. 1, 2, 3. Uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 slots. Right.
Yes.
Now, then see, where R1 first, starting with the same R1, R2, R3. Okay. Now, where R1 dash, R2 dash, it will be at the bottom layer from 9th slot, not 10th.
Yes.
R1 dash, R2 dash, R3 dash. Okay.
Yes, sir.
9, 10, 11. And then where Y1, compulsory 120. R1 to Y1 120 means 7th slot. Y1, Y2, Y3. They must be. Okay.
Yes, sir.
Where Y1 dash,
15, 16, 17.
bottom layer. Y1 dash, Y2 dash, Y3 dash. 15, 16, 17. Okay. And where B1 compulsory 13. B1, B2, B3. Where B1 dash,
3, 4, 5. 3, 4, 5.
B1 dash, B2 dash, B3 dash, 3, 4, 5. That is over now. One set of winding is over. Now where this is started, now I will start here. This is completed now. Here I will start. Here I will start. Which phase? R phase I will start again. R phase. R phase. Now R4, R5, R6. R4, R5, R6. Reverse way you come. Again 180 degrees, 160 degrees. Where it will come, count the angle from here. From here, is there? Here to here. It is how much? 20, 40, 60, 80, 100, 120, 140, 160, 160. But it has kept on the bottom layer. We need to keep in the top layer.
Yes.
R4 started. So this will be here now.
Yes, sir.
12 start. Correct?
Yes, sir.
20, 40,
12
60,
hit.
80, 100, 120, 140, 160. Yes, 12. R4 dash, R5 dash, R6 dash. Over. Next, it will be
B phase.
B phase. B phase. B phase will be R to B exactly. Not R2. Reverse we are coming now.
Yes, sir.
First one RYB. Next RBY. RBY from R to B. R to B. Where it can be R4 to B4 120. 20, 40, 60, 80, 100, 120. Right? The B4 will be here now.
Yes, sir.
B4, B5, B6, B6. And where other side? Again short pitch. Short pitch means
6, 7, 6, 5, 4.
yes. 20, 40, 60, 80, 100, 120, 140, 160. Yes, here. B4 dash, B5 dash, B6 dash, B6 dash. Okay. After that again, Y.
Y phase.
Y phase. B4 to Y4 also 120. 20, 40, 60, 80, 100, 120. So Y4 will start here. Y4, Y5, Y6, Y6. Here other side will be again 160 degrees. 20, 40, 60, 80, 100, 120, 140, 160. Y4 dash, Y5 dash, Y6 dash. This is the winding. Right?
Okay, sir.
Yeah. You can check everywhere it is valid. But another important observation, if you compare these two, what was happened? These stars, if you compare, top layer positions are same, but bottom layer position has shifted left side,
Shifted.
counterclockwise direction. Actually, B1 dash here, R3, everywhere the position has been shifted. Okay?
Yes, sir. Counterclockwise.
Counterclockwise direction. Left side. That is the point I have given there. Because I cannot draw all these things. If I draw all these things, the student, first of all, the syllabus is a file difficult. Because I have at the beginning 2003, this question was given. And after that, I have drawn all PS Bimbra, this concept is available. You see.
Okay. Sir, my one problem, sir, that why when we are putting second layer, sir, when we are putting second layer,
whatever I have drawn, just like that, if you keep on going, you cannot get it. Simple like that. This clockwise and you have to want counterclockwise. This diagram.
When we will start counterclockwise, we will start from that portion from where we are ending. Where we are ending the B layer, we have to start from there only.
Yes, exactly. B when completed, immediately from there onwards, you have to start in counterclockwise.
Okay, sir. One more question, sir.
This is complete. I will take this photo also. One of the students also, he has asked this. The problem is, let me take this photo also. Or can you draw that? You have taken this diagram?
Yes, sir. Yes, sir. I will forward to you, sir.
You forward to me. Or else you can draw your own analysis and still you can draw very clearly, neatly. You can send it to me. So some other people are asking, simply I will forward, because these things only those you have worked out. That's the reason you are showing interest. When I am explaining, you should be very curious. In the class, if I say without anything, if I draw all the things up, the people will link. They will miss the link. Oh, what is this? First they will see. That's the reason shortcut I have given directly. The statement, content I have given, that is fine. Okay.
Yes,
tell me
one more question.
Sir,
that in phasor diagram you was telling yesterday, sir, that. Wait, sir.
Phasor diagram?
Phasor of E and current you was telling now, yes, sir, that EM will be maximum in that conductor which is facing the pole, north pole and south pole. But that phasor will be 90 degree. I am not getting that, sir.
You want which power factor?
Sir, 0.8 lagging you can take.
This is north pole, south pole. Okay. One conductor I am taking. Flux is like this. Flux. It is coming. Okay, this is the flux. Therefore, I can take this is the phi m. Phi m will be in this direction. Phi m or Fm. Okay, air gap flux. In which direction air gap flux was there? Main field flux in this direction. Due to that, in this conductor is rotating counterclockwise direction if you take, under north pole dot, south pole cross. Correct?
Yes, sir.
Because it is clockwise if you rotate, north pole cross, south pole dot. Counterclockwise. This is E maximum here only. Correct?
Yes.
Instantaneous value. If that instant is maximum, no?
Yes, sir.
When conductor is under the pole, it cuts it by 90 degrees. Okay. 90 degrees maximum. And where current will be maximum, if you take for 0.8 lagging, where current lag maximum, 36 degrees it will lags. On space, phase angle, space angle same. On space, two pole machine coverage. This is also, I can take current is lagging here.
But actually here that conductor will be there, sir.
Huh?
Actually here conductor will be there, or we are taking it.
No, conductors are totally distributed throughout the periphery.
Yes, sir. In that conductor which is 36
Even,
degree lagging, in
Huh?
that will be maximum.
huh?
Current
What is
will be
that?
maximum in that conductor which is 36 degree lagging from this
Ah,
position.
yes, yes. That is only the meaning, na? Current. And
Yes,
it
sir.
is dot. Current maximum. A dot of the current lags the dot of the voltage by 90 degrees. Cross of the current lags this cross by 36 degrees. The 5.
Yes, sir.
Okay. Lagging. Both are rotating. Na? This is moving in this direction. Current is moving in this direction. And voltage also moving in this direction.
Yes, sir.
Right. Now to draw the phasor, what to do? What apply the thumb rule, that's all. Thumb rule. These are the instantaneous. Phasor means thumb rule. EMF always here only, na, under north pole cross. Apply, entering, leaving. I can say this EMF phasor here only always. It is always along the Q axis only. Correct? Under north pole cross, under the pole EMF is maximum. Then you apply, it will be along the quadrature axis. That is the phasor of EMF. And current phasor, apply again thumb rule, entering, leaving. This will be the MMF. This is itself FEA and IA also here.
Okay, sir.
IA phasor, to draw the phasor, apply the thumb rule. This current is there. Current will produce the MMF. MMF is a space vector. Current is a
Sir,
time
now
phase.
that induced pole will also change, sir,
Where induced pole?
on the armature, sir.
Yeah, they will change, of course.
In that direction it will be south there, upper, and here north and below.
Yes.
It will be like this.
Yeah.
Sir, and when it will be more than 90 degree, then they will align, sir. North and south will align, sir.
For which power factor?
For lagging power factor, sir.
ZPF
Zero
lagging
lagging.
you want to take, huh? ZPF lagging if you take. ZPF lagging. You take for ZPF lagging. ZPF lagging current will be maximum here, IA maximum. Okay. Here IA maximum done. Then what is the current? This will be the current direction, IA maximum. When this is the current means which pole will form here? Armature poles if you take. This north pole will form, north pole and south pole both will align.
Yes, sir.
Then what is the torque, tell me? 0.
Yes, sir. That only I was saying.
Electromagnetic torque is equal to Fm and angle between these two. Torque 0 only. What is the power? Also 0. Why? Because power factor is 0. Na? There is no angle between these poles. Electromagnetic torque is equal to minus P by 2 mu naught pi RL by G F1, Fm and Fa sin lambda. Okay, sin lambda. But what is the lambda between Fm and Fa?
180.
180. Correct. This is Fm and this is Fa.
Yes, sir.
180. Then what is the sin 180 means?
0.
No torque.
Yes, sir.
There must be some angle. Then only they will repel or attract.
Yes, sir. After this, there will be no synchronism and they will stop, sir. Okay, sir. Thank you.
Okay. Right.
Thank you.
You send that copy, after drawing. Okay.
Yes, sir. I will send.
Okay. I am closing the session. Good night.